Chapter 4, Unit 4, Computer Systems and Networks. 4.1. The Internet, Purpose, History, and Growth. Let's start with a question that sounds simple but trips up more students than you'd expect. What is the Internet exactly? Not your Wi-Fi, not your browser, not Google, the Internet itself. According to the College Board, the Internet is a computer network that consists of interconnected networks that use standardized open communication protocols. That definition has teeth on the AP exam, so let's unpack it carefully. What the Internet actually is. Picture a city's road system. You have local streets, connecting roads, highways, and interstate systems, all built by different organizations using different materials, but all following the same rules about lane widths, signage, and traffic laws so that any car can travel anywhere. The Internet works the same way. Billions of devices, thousands of networks owned by universities, corporations, governments, and individuals, all agreeing to speak the same language. That shared language is called a protocol, and the foundational protocol suite of the Internet is TCP/IP, or Transmission Control Protocol, Internet Protocol. Here's where students get their first common trap wrong on the exam. The Internet is not the same as the World Wide Web. The Internet is the physical and logical infrastructure, the roads. The World Wide Web is one application that runs on top of that infrastructure, one type of vehicle using those roads. Email, video streaming, online gaming, these are all separate applications that also use the Internet. If an MCQ asks whether the web is the Internet, the answer is no. The web is a service that uses the Internet. The history and purpose. ARPANET and fault tolerance. The Internet didn't appear overnight, and understanding its origins tells you something crucial about its design philosophy, something the AP exam tests directly. In the late 1960s, the U.S. Department of Defense funded a research project called ARPANET, Advanced Research Projects Agency Network. The original engineers had a very specific goal: build a communication network that could survive partial failure. Think about it from a Cold War perspective. If enemy missiles destroyed key communication hubs, how could you keep information flowing? The answer was brilliant in its simplicity. Design the network so that data can route around damage. This idea gave birth to packet switching, which is one of the most exam-critical concepts in this entire unit. Instead of sending a message as one continuous signal down a dedicated line, like a phone call, packet switching breaks data into small chunks called packets. Each packet travels independently through the network, potentially taking completely different paths to reach the same destination, and then gets reassembled at the other end. Think of mailing a novel by tearing out each chapter and putting each in a separate envelope. Different envelopes might take different postal routes. Some might arrive out of order, but as long as they all arrive, you reassemble the book. Why does this matter so much? Because it means no single point of failure can bring down the whole network. If one router or connection goes down, packets just find another path. This fault tolerance is a core design principle of the Internet, and the AP exam loves asking about it. You should know that the Internet was intentionally designed to be redundant and decentralized for exactly this reason. Growth and scale. How the Internet expanded. From ARPANET's handful of connected universities in 1969, the Internet grew into a global system connecting billions of devices. A few milestones worth knowing. In the early 1990s, Tim Berners-Lee invented the World Wide Web, that layer of hyperlinked documents on top of the Internet, which opened it to general public use and drove explosive growth. The number of Internet users, websites, and connected devices has grown exponentially over the decades. A pattern you should be able to describe conceptually. If a graph question shows the number of Internet hosts plotted over time, expect a curve that starts flat and then rises steeply, classic exponential growth. The AP exam won't ask you to calculate exponential growth with a formula, but you should recognize and describe that pattern and explain that the adoption of open, standardized protocols is a key reason for such rapid expansion. Scalability and open protocols. Here's a concept the College Board emphasizes heavily. The Internet grew as fast as it did because its protocols are open standards, meaning anyone can implement them without paying licensing fees or getting special permission. This is not an accident. It's a deliberate design choice that allowed innovation to flourish from every corner of the world. Compare this to a proprietary system where one company controls the rules. Growth would have been much slower and more centralized. When the exam asks why the internet was able to scale globally, your answer should center on open protocols and decentralized design. The term scalability means the system can keep working effectively as it grows larger. The internet is highly scalable because adding new devices or networks doesn't require rebuilding the whole system. They just need to agree to follow the same protocols. This connects directly to Unit 5 concepts around beneficial and harmful effects of computing, where you'll discuss how the internet's open design created enormous economic and social opportunity, but also introduced challenges like security vulnerabilities and the digital divide. Common MCQ traps to watch for. Let's talk about the traps because this section has several. First, students often confuse the internet with the web. We've covered that. Second, many students think the internet has a central controlling authority. It does not. It is managed through a distributed system of organizations and agreements, not a single government or company. Third, watch out for questions that imply the internet was designed primarily for speed or cost efficiency. It was primarily designed for reliability and fault tolerance. Speed and efficiency came later as priorities. A fourth trap involves packets. Some students think packets from the same message always travel the same path. They don't. Packets from a single message can take different routes and arrive out of order, and that's normal and expected behavior in packet switching networks. Connections to other units. Understanding the internet's purpose and design gives you the foundation for everything else in Unit 4, how data moves across networks, how cybersecurity vulnerabilities arise from the same open design that enables growth, and why the internet creates both opportunity and risk. It also connects to Unit 2's discussions of data representation, because packets are ultimately just binary data traveling through physical and wireless media. And it connects to Unit 5's impact discussions, where the internet's global reach raises questions about equity of access, surveillance, and innovation. With the big picture of what the internet is and why it was built the way it was now firmly in your mind, you're ready to zoom in on the mechanic, how data actually travels across this remarkable system, which means it's time to explore network protocols, routing, and the architecture that makes it all work. 4.2 How the Internet Works, Packets, Routing, and Protocols. The big picture, a network of networks. Let's start with a mental image. Imagine you're trying to send a birthday cake from New York to Los Angeles. You can't just hand it to one person and say, "Take this to California." Instead, you'd break it into pieces, box each piece separately, label every box with the destination address and a number, so the recipient knows how to reassemble it, and send those boxes through a series of distribution centers, each one deciding the best next stop. That, in a nutshell, is how the internet moves your data. The cake pieces are called packets, the distribution centers are called routers, and the rules governing how everything gets labeled, sent, and reassembled are called protocols. The College Board expects you to understand all three of these ideas deeply, not just what they are, but how they interact and why they're designed the way they are. Packets and packet switching. When you send a message, watch a video, or load a web page, your device doesn't blast one giant continuous stream of data across the internet. It breaks that data into small, manageable chunks called packets. Each packet contains a piece of the actual data, called the payload, along with header information, specifically the source address, the destination address, and sequence information so packets can be reassembled in order on the other end. This approach is called packet switching, and it's one of the most important design choices the AP exam wants you to understand. Packet switching means that different packets from the same message can travel along completely different paths through the network and still arrive at the destination where they get put back together. Compare this to a phone call, which uses something called circuit switching, where a dedicated connection is held open for the entire duration of the call. The AP exam loves to contrast these two. Packet switching is more fault-tolerant and efficient because it doesn't tie up a single path. If one route is congested or broken, packets can be rerouted automatically. Circuit switching is more predictable but wasteful. For the exam, remember, the Internet uses packet switching, and this is a deliberate feature, not an accident of history. Routers and routing. Now let's talk about those distribution centers, the routers. A router is a device that sits at the intersections of the Internet and decides, for each incoming packet, which direction to send it next. Think of a router as a really good GPS system that doesn't plan the whole trip at once. It just says, from here, your next turn is left. Each router maintains a routing table, which is basically a map of neighboring routers and the best paths to various destinations. When a packet arrives, the router reads its destination address and forwards it one hop closer to where it needs to go. This is why the Internet is considered decentralized. No single computer controls all the routing decisions. Every router makes its own local decision, and the packet hops from router to router until it reaches its destination. The AP exam will sometimes ask you why this decentralized design is important, and the answer ties directly back to fault tolerance. If any single router fails, packets get rerouted around it. There's no single point of failure that can bring down the whole system. This was actually a key design goal of ARPANET, the Internet's predecessor, developed to maintain communication even if parts of the network were destroyed. Protocols, the rules that make it all work. Here's where students sometimes get fuzzy, so let's be precise. A protocol is simply an agreed-upon set of rules for how data is formatted, transmitted, and received. Without protocols, a computer from one manufacturer couldn't talk to a computer from another manufacturer. It would be like two people trying to have a conversation in different languages. The Internet works because everyone agrees to follow the same rulebooks. The two most critical protocols for this exam are IP Internet Protocol and IP-TCP Transmission Control Protocol, and they're often written together as TCP/IP. Here's how to think about them separately. IP handles the addressing and routing. It's what puts the source and destination addresses on each packet and allows routers to forward them correctly. Every device on the Internet has an IP address, which is its unique identifier on the network. TCP handles reliability and order. It ensures that all packets arrive, checks for errors, and requests retransmission of any packets that get lost or corrupted. If IP is the addressing system on the envelope, TCP is the postal service guarantee that makes sure everything actually got there intact. The AP exam also wants you to know about HTTP Hypertext Transfer Protocol and HTTPS, which operate at a higher level. HTTP is the protocol your browser uses to request and receive web pages. HTTPS adds a layer of encryption. The S stands for secure, which is why you see that padlock in your browser's address bar on reputable websites. For the exam, know that HTTPS protects the data in transit from being intercepted and read by a third party, which connects directly to Unit 5 concepts around cybersecurity and privacy. Common MCQ traps to watch out for. The College Board has a few favorite tricks in this section. First, don't confuse bandwidth with speed. Bandwidth is the maximum amount of data that can be transmitted per unit of time. Think of it as the width of a highway. More bandwidth means more lanes, not necessarily faster travel. A common wrong answer will conflate the two. Second, many students incorrectly believe that packets from the same message always travel the same path. They do not. Each packet is routed independently based on network conditions at that moment. Third, watch for questions about what happens when a packet is lost. Under TCP/IP, the receiving device detects the loss and requests retransmission. The data isn't simply gone forever. Finally, be careful with questions that describe the Internet as having a central authority or a single point of control. It doesn't. That's the whole point of its decentralized architecture. Connections to other units. Understanding how the Internet works is the foundation for several other topics you'll encounter. In Unit 5 on cybersecurity, you'll return to protocols like HTTPS when discussing encryption and data protection. The concept of fault tolerance connects directly to Unit 4's broader themes about reliable system design. And when you study data compression later in the course, remember that compressed data still travels as packets. The compression just makes those packets smaller and faster to transmit. Everything you learn in this section is scaffolding for what comes next. Speaking of what comes next, now that you understand how data moves across the internet, it's time to zoom out and think about how the internet's structure enables something equally fascinating: the explosive growth of the World Wide Web and the way information is actually found, organized, and accessed online. 4.3 IP addresses and DNS. The Internet's postal system. Let's start with a picture you already understand. Imagine you want to send a letter to a friend across the country. You need two things: their street address, so the postal service knows where to deliver it, and ideally their name so they know it's for them. The Internet works almost exactly the same way. Every device connected to the Internet has a numerical address, and a system exists to translate human-readable names into those numbers. That's the heart of Section 4.3, and once you understand the analogy, the rest falls into place beautifully. What is an IP address? An IP address, short for Internet Protocol Address, is a unique numerical label assigned to every device participating in a computer network that uses the Internet Protocol for communication. Think of it as your device's home address on the Internet. Without it, data packets would have no idea where to go. Now, the College Board expects you to know two versions of IP addressing: IPv4 and IPv6. IPv4 addresses are the classic format: four groups of numbers separated by dots, like 192.168.1.1. Each of those four groups is called an octet because each one is 8 bits, giving you a range from 0 to 255 per group. 4 octets times 8 bits each means IPv4 uses 32 bits total. Here's the critical calculation you must be able to do. The total number of possible IPv4 addresses is 2 to the power of 32, which equals approximately 4.3 billion addresses. When the Internet was young, that seemed like more than enough. Spoiler, it wasn't. IPv6 was developed precisely because we ran out of IPv4 addresses. IPv6 uses 128 bits instead of 32, written as 8 groups of 4 hexadecimal digits separated by colons, something like 2001, 0DB8, 085A 3000008, a 2E, 0370 CAN 7334. The number of possible IPv6 addresses is 2 to the power of 128, a number so astronomically large that we genuinely will not run out. For the AP exam, you need to know the bit lengths: 32 for IPv4, 128 for IPv6, why IPv6 was created, address exhaustion due to Internet growth, and that IPv6 allows for vastly more unique addresses. You do not need to memorize specific address formats in detail, but you absolutely need to understand the scalability argument. The common MCQ trap on IP addresses. Here's where students lose points. The exam will sometimes ask whether IP addresses are hierarchical or flat. IP addresses are actually hierarchical. The first portion of an IP address identifies the network, and the later portion identifies the specific device within that network. This hierarchy is what makes routing efficient. Routers don't need to know every single device on the Internet, they just need to know which network to forward traffic toward. Think of it like a zip code system. Your mail carrier doesn't need a map of the entire country, just your neighborhood. If an exam question suggests IP addresses are random or non-hierarchical, that's your red flag. Another trap: students confuse IP addresses with MAC addresses. A MAC address is a hardware-level identifier burned into your network card. It's permanent and local. An IP address is a logical software-assigned address that can change and works across networks. The AP exam loves asking which one is used for internet-wide routing. The answer is always the IP address. What is DNS and why does it matter? Now, let's meet the translator. DNS stands for Domain Name System, and it is essentially the Internet's phone book. When you type google.com into your browser, your computer has no idea what that means at the network level. It needs a number, an IP address. DNS is the system that translates human-friendly domain names like google.com into machine-readable IP addresses like 142.250.80.46. Here's the real-world story that makes this click. Imagine you want to call your friend Sarah, but you only know her name, not her phone number. You look her up in a directory, get her number, and dial. You connected to Sarah, not the directory. The directory just helped you find the right number. DNS works identically. Your browser contacts a DNS server, asks, "What's the IP address for google.com?" gets an answer, and then connects directly to Google's server. The DNS server itself is not involved in your actual web browsing session. It just performed the lookup. The College Board describes DNS as an example of abstraction. Domain names are an abstraction layer on top of numerical IP addresses. They hide the complexity of the underlying system and make the Internet usable for humans. This connection to the concept of abstraction, which you studied in Unit 3, is a genuine cross-unit link, the exam test. DNS is also a beautiful example of how the Internet was designed to be scalable and decentralized. There isn't one giant DNS server holding every domain name. The system is distributed across many servers worldwide, which makes it both fault-tolerant and fast. How DNS resolution works. The AP exam wants you to understand the basic process, not every technical detail. When your device needs to resolve a domain name, it first checks its local cache, a temporary memory of recent lookups. If the answer isn't there, it contacts a DNS resolver, usually provided by your Internet service provider, which then queries a hierarchy of DNS servers until it finds the answer. This result is then cached for a period of time to speed up future requests. The key vocabulary here is DNS resolution, the process of converting a domain name to an IP address, and you should be comfortable describing it in plain language on a free response question. Connections to other topics. IP addresses and DNS connect to several other parts of the course. In your study of the Internet's architecture, you learned that the Internet is a packet switching network, and every packet needs a destination IP address to be routed correctly. DNS is what makes those destinations human accessible. You'll also see connections to cybersecurity. DNS spoofing is a real attack where malicious actors corrupt the DNS lookup process to redirect users to fake websites, which ties directly into the security concepts in Unit 5. Understanding that DNS is a trusted intermediary helps you understand why corrupting it is so dangerous. The big exam day reminder: when a question mentions that a user cannot connect to a website by name but can connect using the IP address directly, that is a classic symptom of a DNS failure, not a network failure. The routing infrastructure is fine, the translation service is broken. Recognizing that distinction is exactly the kind of nuanced thinking that separates a 4 from a 5. With your mental map of IP addresses and DNS firmly in place, you're perfectly set up to explore how all this data actually travels across networks. Which brings us right to our next topic, the protocols and fault-tolerant design that keep the Internet running even when parts of it fail. 4.4 TCP/IP and HTTP/HTTPS. The Internet's secret handshake. All right, let's talk about how the Internet actually works under the hood. Not the glossy, you type a URL and a web page appears version, but the real story. Because on the AP exam, College Board wants you to understand the protocols that make global communication possible, and this section is one of the most concept-dense in the entire course. So grab your coffee and let's dig in. What is a protocol, and why does it matter? Start here. A protocol is simply an agreed-upon set of rules for communication. That's the College Board definition, and you need to have it ready. Think of it like this. When you call a friend, there's an informal protocol. The phone rings, they say hello, you say who you are, you talk, you say bye. Without that shared understanding, the conversation breaks down. The Internet works the same way, just with incredibly precise rules enforced by software. The collection of protocols that governs the Internet is called TCP/IP, which stands for Transmission Control Protocol and Internet Protocol. These two work together so constantly that we say them as one thing, like a duo. IP is the addressing system. It handles where data is going. TCP is the delivery system. It handles how data gets there reliably. IP, the postal address of the Internet. Here's the analogy that makes IP click. Imagine you're mailing a letter. You need the recipient's address on the envelope. IP addresses are exactly that, numerical labels assigned to every device on a network. Your computer, your phone, your smart TV, they all have one. When data travels across the internet, it's broken into smaller chunks called packets, and every packet gets stamped with both a source IP address and a destination IP address. Think of each packet as a separate envelope carrying part of your message. Here's a detail that trips up students on the MCQ. Packets can take different routes to reach the same destination. This is not a bug, it's a feature. The internet is designed to be redundant, so that if one path goes down, data finds another way. This is actually one of the original design goals of the internet, rooted in its ARPANET origins. If you see a question asking whether packets must travel the same path, the answer is no. And if a question asks what happens when a router on the path fails, the answer is that packets are rerouted, the communication TCP, making sure everything arrives. IP gets your packets moving in the right direction. But it doesn't guarantee they'll arrive or that they'll arrive in order. That's where TCP enters the picture. TCP is connection-based and adds reliability through a process called the three-way handshake. Before data transfer begins, the two devices essentially say, "Ready, ready, let's go." This establishes the connection. Then, as data is sent, TCP numbers each packet sequentially and requires the receiver to send back acknowledgments. If a packet gets lost or corrupted, TCP requests it again. If packets arrive out of order, TCP reassembles them correctly. It's like a meticulous postal worker who won't mark a package delivered until you personally sign for it. The exam loves testing whether you understand the trade-offs here. TCP is reliable but slower because of all that back and forth checking. You'll sometimes see questions contrasting TCP with UDP, User Datagram Protocol, which prioritizes speed over reliability. Streaming video or gaming often uses UDP because a slightly glitchy frame is better than frozen video. TCP is used for web browsing, email, and file transfers, where accuracy matters completely. Know this distinction cold. HTTP and HTTPS, the language of the web. Now, TCP/IP is the infrastructure. HTTP Hypertext Transfer Protocol is the language your browser and a web server use to talk to each other on top of that infrastructure. When you type a URL and hit enter, your browser sends an HTTP request to the server, asking for specific content. The server sends back an HTTP response containing the data, the HTML, images, whatever you asked for. It's a request-response model, every single time. The critical upgrade to HTTP is HTTPS, where the S stands for secure. HTTPS uses encryption, specifically a protocol called TLS, Transport Layer Security, sometimes called SSL, to protect the data being exchanged. Here's the everyday analogy. HTTP is like mailing a postcard. Anyone who handles it along the way can read it. HTTPS is like putting that postcard in a sealed, tamper-evident envelope that only the intended recipient can open. If someone intercepts the data mid-transmission, they see scrambled, unreadable ciphertext. This matters enormously for things like passwords, credit card numbers, and personal information. On the exam, you should know that HTTPS provides confidentiality. The data can't be read by eavesdroppers. Integrity, the data hasn't been altered in transit. And authentication, you're actually talking to the real server, not an impersonator. A common MCQ trap is suggesting that HTTPS makes your device secure from all threats. It does not. HTTPS secures the transmission, not your device itself. Malware on your computer is a separate problem. The layered model, abstraction and action. Here's where this connects beautifully to other units. Remember the concept of abstraction from Unit 1? TCP/IP is a perfect example of layered abstraction in networking. HTTP doesn't need to know how TCP moves the data, it just trusts that it will. TCP doesn't need to know about IP routing, it just passes packets down. Each layer handles its own job and hides complexity from the layers above. This is why College Board asks you to understand this topic conceptually, not mathematically. You need to know what each layer does and why that separation of responsibilities makes the internet scalable and flexible. Also connect this to Unit 5's cybersecurity content. The shift from HTTP to HTTPS is a direct response to threats like packet sniffing, where attackers intercept unencrypted data on a network, especially dangerous on public Wi-Fi. Understanding that encryption is a protocol-level solution helps you see how security and networks intertwine. Exam traps to avoid. Watch out for these classic wrong answer choices. First, don't confuse IP addresses with domain names. They're related through DNS, domain name system, but they're not the same thing. Second, don't say packets always travel the same path. They don't. Third, don't claim HTTPS prevents all cyber attacks. It prevents interception of data in transit. Full stop. Fourth, students often mix up the roles of TCP and IP. Remember, IP is addressing, TCP is reliability. When you see FRQ questions about networks, use precise vocabulary, write packets, write protocols, write request-response model. College Board scoring rubrics reward exact terminology, and vague answers like, the internet sends the information, won't earn points. With that solid foundation in how data moves and how it's secured, you're perfectly set up to explore the broader landscape of cybersecurity threats and defenses, which is exactly where we're headed next. 4.5 Network Layers and Abstraction. Why layers? The big idea. Imagine you're sending a letter to a friend across the country. You don't think about the postal sorting facility in Memphis, the logistics network that decides whether your package goes by truck or plane, or the neighborhood carrier who walks their route in the rain. You just write the letter, seal it, and drop it in the mailbox. That separation of concerns, where each layer handles its own job without you needing to understand the details, is exactly what abstraction does in computer networks. And that concept is at the absolute heart of Section 4.5 for the AP exam. The College Board wants you to understand that the Internet is not one giant monolithic system. It's a collection of layers of abstraction, each one building on the one below it, each one hiding complexity from the layer above. This is one of the most powerful ideas in all of computer science, and you'll see it tested repeatedly, both in multiple choice and in the performance task context. The layers themselves. The AP exam doesn't ask you to memorize the full 7-layer OSI model the way a networking course might. Instead, it focuses on a simplified 4-layer model that maps to how the Internet actually works. Think of these 4 layers as 4 departments in a very well-organized company. The bottom layer is the Internet hardware layer, sometimes called the link layer or physical layer. This is the world of cables, fiber optics, Wi-Fi signals, and the actual electrical or optical pulses that carry data. You don't need to know how to wire a router, but you do need to understand that this layer exists and that it provides the physical pathway for everything else. Above that sits the Internet layer, which handles addressing and routing. This is where IP, the Internet Protocol, lives. Think of IP addresses like street addresses on your letter. The Internet layer doesn't care what's inside your envelope. It just makes sure the package gets from point A to point B by figuring out the best route through a maze of interconnected routers. Each router along the way reads the IP address and makes a local decision about where to send the packet next. No single router knows the entire path. They each just know the next step. That decentralized routing is crucial for the exam because it connects directly to Unit 4's concept of fault tolerance. If one path goes down, packets can reroute around the problem automatically. The next layer up is the transport layer, home to TCP, the Transmission Control Protocol, and also UDP-TCP, is the careful, responsible sibling. It breaks your data into packets, numbers them, sends them, confirms they arrived, and requests retransmission of anything that got lost. UDP is the fast, reckless sibling. It sends packets without confirmation. For the AP exam, you need to know that TCP is used when accuracy matters, loading a web page, sending an email, downloading a file, and UDP is used when speed matters more than perfection. Live video streaming, online gaming, voice calls. A dropped frame in a video call is annoying. A web page that silently loads half its data is a disaster. At the very top sits the application layer, which is where protocols like HTTP web browsing, HTTPS secure web browsing, FTTP file transfer, and its HTTPS secure web browsing, FTP file transfer, and DNS domain name system live. This is the layer you as a user interact with, even if you don't realize it. When you type a URL into your browser, DNS translates that human-readable name into an IP address. That's the application layer talking to the internet layer. Notice how elegant that is. Each layer just calls on the one below it when it needs something done. Abstraction in action. Here's the key exam insight you need to lock in. Each layer only communicates with the layers directly above and below it. The application layer doesn't need to know whether your data is traveling over fiber optic cable or Wi-Fi. The hardware layer doesn't need to know whether you're loading Instagram or sending an email. This isolation is what makes the entire internet scalable and modifiable. You can upgrade the physical infrastructure without rewriting every application. You can invent a new application protocol without redesigning how packets are routed. This is abstraction doing its most powerful work. The College Board loves to test this with questions that describe a change at one layer and ask what it affects. The correct answer is almost always only that layer, unless the question specifically describes an interface between layers changing. Watch for this trap carefully. Common MCQ traps and how to dodge them. One of the most common traps involves confusing IP addresses with domain names. IP addresses are numerical identifiers used at the internet layer. For example, 132.168.1.1. Domain names like www.example.com are human-friendly aliases resolved by DNS at the application layer. These are not the same thing, and questions will try to get you to conflate them. Another trap involves the word protocol itself. The AP exam defines a protocol as an agreed-upon set of rules that specify the behavior of a system. Students sometimes think a protocol is a piece of software you install, but it's really just a shared agreement, like the rules of a language that two parties both speak. HTTP is a protocol. Your browser is software that implements that protocol. Know the distinction. You'll also see questions about packet switching versus older circuit switching models. The Internet uses packet switching, meaning data is broken into small chunks, packets. They can take different routes and reassemble at the destination. This is fundamentally different from a phone call on an old telephone network, where a dedicated circuit was held open for the entire conversation. Packet switching is more efficient and more fault-tolerant because it doesn't rely on any single path being available. Connecting to other units. This topic is a beautiful bridge between several other parts of the course. The layered abstraction model is a direct application of the abstraction concepts you studied in Unit 3, where procedures and libraries hide complexity from the programmer. The fault tolerance enabled by packet switching and decentralized routing ties directly into your work on redundancy and system reliability. And when you hit Unit 5's discussions of cybersecurity, you'll see that protocols like HTTPS exist specifically because the earlier HTTP protocol at the application layer had no built-in security, which is exactly the kind of layer-specific vulnerability that attackers exploit. Understanding that security must be designed into a layer, not assumed, is a deeply testable idea that bridges Units 4 and 5 seamlessly. One mental model to rule them all. If you can remember just one thing about network layers for the exam, let it be this: abstraction hides complexity and allows each layer to change independently. Every question about protocols, every question about what happens when a router fails, every question about why the internet was designed the way it was, all of it flows from that single principle. The layers are not a bureaucratic inconvenience. They are the engineering genius that made a global, resilient, scalable network possible. As we move into our next section, you'll see how these network principles connect to the even broader questions of how the internet enables new kinds of collaboration and the ethical responsibilities that come with building systems at this scale. 4.6 Open Protocols and Standards. Let's talk about something that might seem dry on the surface, but is actually one of the most important ideas in all of computing, and one that shows up on your AP exam in ways students consistently mishandle. We're talking about open protocols and standards, and once you really understand what these are and why they exist, you'll see fingerprints of this concept everywhere. What is a protocol, and why does open matter? Start with the word protocol. A protocol is simply an agreed-upon set of rules for how communication happens. Think about what happens when two people meet for the first time. There's an unspoken protocol. You make eye contact, extend your hand, say your name, wait for the other person to respond. Nobody invented that in the moment. It's a shared convention that makes the interaction possible. Computer protocols work exactly the same way. They define how devices send messages, how they format data, how they handle errors, how they know when the other side received something correctly. Now add the word open. An open protocol is one where the rules are publicly available, published, documented, and accessible to anyone without needing special permission or paying licensing fees. The opposite would be a proprietary protocol, which is owned and controlled by one company and kept secret or restricted. Here's why this distinction is enormously consequential. When protocols are open, anyone can build software or hardware that follows those rules, which means devices from completely different manufacturers, running completely different operating systems, written by engineers who have never met, can all communicate with each other seamlessly. That's not magic. That's the power of shared open standards. The Internet as a living example. The greatest real-world example of open protocols working at scale is the Internet itself. The Internet runs on a collection of open protocols, and the College Board specifically wants you to know a handful by name. The most fundamental is the Internet Protocol, or IP, which handles addressing essentially the postal system of the Internet. Every device gets an IP address. An IP defines how data gets packaged into packets and routed from source to destination. Paired with IP is TCP, the Transmission Control Protocol. TCP handles reliability. It makes sure packets arrive, checks for errors, and requests retransmission when something goes wrong. You'll often see these written together as TCP IP, and the AP exam treats this pair as the backbone of Internet communication. Then there's HTTP, Hypertext Transfer Protocol, which is what your browser uses to request web pages. When you type a URL and hit enter, your browser sends an HTTP request, and the server responds with HTTP as well. The secure version, HTTPS, adds a layer of encryption on top of that. The College Board also wants you to know DNS, the domain name system, which translates human-readable names like collegeboard.org into IP addresses that computers can actually route to. Think of DNS as the Internet's phone book, except it's constantly updated and distributed across thousands of servers worldwide. Here's a critical connection for the exam. All of these protocols work because they are open. Any engineer, anywhere, can read the specification for HTTP and build a web server or a browser that follows it. This is why Firefox can talk to an Apache web server, even though Mozilla and the Apache Software Foundation have no direct relationship. The open protocol is the handshake they both agreed to in advance. Standards, bodies, and the role of interoperability. The AP exam cares about why open standards matter, not just what they are. The key concept here is interoperability, the ability of different systems, devices, and software to work together. When you plug any USB device into any computer, that works because USB is an open standard. When you send an email from Gmail to an Outlook inbox, that works because email protocols like SMTP are open. Without open standards, you'd live in a world where you could only email someone who used the exact same email provider as you, which is actually how some early proprietary networks worked before the Internet replaced them. There's also an important equity and access argument baked into this. Because open protocols are publicly documented and free to implement, they lower the barrier to entry for innovation. A small startup or a developer in any country can build a product that connects to the Internet without asking anyone's permission. This is directly tied to what the AP curriculum calls the democratizing effect of the Internet. It enables participation from people who wouldn't otherwise have access to the infrastructure. Common MCQ traps to watch for. The exam will try to trip you up in a few predictable ways. First, watch out for questions that conflate open with free of charge. An open protocol means the specification is publicly available and unrestricted. It doesn't necessarily mean that every product built using that protocol is free. Be precise with that definition. Second, students sometimes confuse protocols with physical hardware. The protocol is the set of rules, not the cables or chips. TCP/IP is software-level logic. It can run over fiber optics, Wi-Fi, or satellite. The protocol doesn't care about the physical medium below it. This layered thinking is exactly how the Internet is designed, and it's a concept the AP exam tests regularly. Third, be careful with questions about what happens when proprietary systems replace open ones. The exam often asks you to reason about consequences. If a company replaces an open protocol with a proprietary one, what happens? The answer involves reduced interoperability, potential lock-in, and barriers to competition. Practice that line of reasoning. Connections to other units. This topic doesn't live in isolation. It connects directly to Unit 4's broader discussion of how the Internet works, including routing, fault tolerance, and packet switching, which you covered earlier. It also connects to Unit 5's treatment of the impact of computing, where questions about innovation, access, and equity show up. The idea that open standards enable collaboration and reduce gatekeeping is part of the larger story the AP course tells about computing as a tool for human progress. And when you get to cybersecurity topics, you'll see that open protocols create both opportunity and vulnerability because anyone can read the specification. Bad actors can too. Understanding how HTTPS addresses some of that vulnerability by adding encryption on top of HTTP is a connection worth keeping in mind. Open protocols are the grammar of the Internet, invisible when they work, catastrophic when they break down or disappear. Keep that metaphor with you, and you'll be well prepared when the exam asks you to think about what makes global communication possible in the first place. Next, we'll look at how all this data actually moves across that network, diving into the mechanics of fault tolerance and how the Internet is designed to stay functional even when parts of it fail. 4.7 Fault tolerance. Let's talk about something that affects you every single day, even though you probably never think about it. Right now, somewhere in the world, a hard drive is dying. A fiber optic cable is getting accidentally cut by a construction crew. A server is overheating. And yet your email still works. Your bank account is still accessible. Netflix is still streaming. How? The answer is fault tolerance, and it's one of the most elegant ideas in all of computer science. What fault tolerance actually means. The College Board defines fault tolerance as the ability of a system to continue operating properly even when some of its components fail. Notice that phrasing carefully: continue operating, not restart after it fails, not warn you that something broke, but keep going as if nothing happened. That distinction is important for the exam. Fault tolerance is about maintaining functionality in the presence of failure, not recovering from failure after the fact. Think of it like your car. You have one engine, but you have 4 tires. If one tire blows out on the highway, your car doesn't stop working entirely, it limps along, or you pull over safely and swap the spare. The system was designed with redundancy, extra capacity built in specifically to handle failure. That's the core idea. Redundancy is the primary mechanism by which systems achieve fault tolerance. Redundancy, the heart of the concept. Redundancy means having more components than the minimum needed to function. And here's where the AP exam loves to test you. Redundancy doesn't just mean having a backup. It means the backup is already active and available. So when something fails, users don't even notice. Here's the analogy I want you to lock in. Imagine a bridge over a river. A single-lane bridge is not fault-tolerant. If something blocks it, all traffic stops. But a 4-lane bridge? If one lane is closed, traffic keeps flowing. You've built in redundancy. The system degrades gracefully rather than failing completely. The College Board specifically wants you to understand this in the context of network. The Internet itself was designed with fault tolerance in mind. This is actually part of its origin story as a military communication network that needed to survive partial destruction. Data is broken into packets, and those packets can travel along multiple different paths to reach their destination. If one router goes down, packets reroute around it automatically. The network has redundant connections, meaning there is more than one path between points. The network diagram. Know how to read and draw it. The AP exam will absolutely show you network diagrams and ask you to evaluate fault tolerance. Here's how you need to think about them. A network diagram shows devices, computers, servers, routers as nodes, and the connections between them as edges. When the exam asks, "Is this network fault tolerant?" what you're really asking is, can every device still communicate with every other device if one connection or one node is removed? The key test is this. If you can remove any single edge or any single node from the diagram and the remaining devices are still all connected to each other, the network has fault tolerance. If removing even one element disconnects any part of the network, it is not fault tolerant. Let's be concrete. Draw 3 devices, call them A, B, and C in a triangle. A connects to B, B connects to C, and C connects to A. That's a redundant, fault-tolerant network. Remove any single connection, and the other 2 still form a path. Now draw a line. A connects to B, B connects to C, nothing else. That's called a linear or chain topology. Remove the middle connection and it can no longer reach C. That network has no fault tolerance whatsoever. The exam loves to show you slightly more complex diagrams with 4, 5, or 6 nodes and ask you to identify which single connection, if removed, would break communication, what networking folks call a single point of failure. Train yourself to hunt for those nodes or connections where everything funnels through one path. Edge cases and exam traps. Here's a trap that catches a lot of students. More connections always means more fault tolerant, right? Not necessarily. What matters is whether all nodes remain reachable, not the raw count of connections. You could have a densely connected network where one particular node is still a single point of failure because several outlying devices only connect through it. Always trace the paths, don't just count the lines. Another common trap. Students confuse fault tolerance with redundancy as if they're the same thing. Redundancy is the mechanism. Fault tolerance is the property. A system achieves fault tolerance through redundancy. On an FRQ, if you're asked to explain how fault tolerance is achieved, you need to mention redundancy specifically, extra components, extra connections, multiple pathways, or you'll lose points. Also, watch out for questions about scale. The College Board may ask what happens when you add redundancy to a system, and the correct answer involves acknowledging that redundancy increases cost, complexity, and resource usage. There's always a trade-off. Fault tolerance isn't free. More redundant paths mean more hardware, more energy, more maintenance. The exam sometimes frames this as, what is a disadvantage of implementing redundancy? And students who only memorize the benefits get tripped up. Connecting to the bigger picture? Fault tolerance connects directly to topics you've seen elsewhere in this course. Back in your study of the Internet structure, you learned that the decentralized packet-switching design of the Internet is itself a fault-tolerant architecture. That's not a coincidence. It's by design. When you get to cybersecurity topics, you'll see that distributed denial-of-service attacks actually try to overwhelm redundant systems until fault tolerance breaks down under sheer volume. Attackers exploit the limits of redundancy. Fault tolerance also connects to the broader theme of how we evaluate systems. When the College Board asks you to assess whether a network or system meets its requirements, fault tolerance is one of the criteria you apply. A system that loses all function when one component fails hasn't met a reasonable reliability standard for critical applications. Hospitals, financial systems, air traffic control. The stakes make the design choices matter. The bottom line for your exam. Fault tolerance means continuing to operate despite failures. Redundancy is how you achieve it, and you test for it by checking whether removing any single component still leaves all other components connected and functional. Trace the paths. Find the single points of failure, and remember that redundancy always comes with trade-offs. With that foundation and reliable systems solidly in place, you're perfectly positioned to explore how we keep those systems not just available, but secure, which brings us right into the world of cybersecurity and the threats that engineers are constantly designing against. 4.8 Redundancy and fault tolerance in networks. Imagine you're driving across town to meet a friend for dinner. You leave early, you know the route, and everything's going fine until you hit an accident that shuts down the main road completely. Now, if that's the only road between you and dinner, you're stuck. But if there are 2 or 3 alternate routes, you just reroute, maybe arrive 5 minutes late, and nobody's meal is ruined. That right there is the core idea behind redundancy and fault tolerance in networks, and it's one of the most elegant practical ideas in all of computer science. What redundancy actually means: the College Board wants you to understand redundancy as the inclusion of extra components that are not strictly necessary for the system to function under normal conditions, but which allow the system to continue operating if one or more components fail. Think of it like a spare tire. You don't need it on a normal day, but the day your tire blows out, that spare is everything. In a network, redundancy typically means having multiple paths between devices, multiple servers holding the same data, or multiple connection points so that if one goes down, traffic can be rerouted through another. The AP exam will ask you to evaluate network diagrams and determine whether a network is fault tolerant. Here's exactly how you think through those questions. A network is considered fault tolerant if there exists at least one alternate path between any two nodes when any single connection or node is removed. When you see a network diagram on the exam, your job is to mentally or physically on your scratch paper remove one connection at a time and ask, can every remaining node still communicate with every other remaining node? If yes for every single possible removal, the network is fault tolerant. If there's even one removal that isolates a node or splits the network into disconnected parts, it is not fully fault tolerant. The language of fault tolerance. Let's be precise about the College Board's terminology, because this is where students lose points. The term fault tolerant means a system can continue operating, possibly at reduced capacity, even when one or more of its components fail. The key phrase is continue operating. Not operate perfectly and not operate without any slowdown. Just continue. A network with redundant paths might route data more slowly around a failure, but it still gets the data there. That's fault tolerance in action. You'll also hear the term reliability in this context. Reliability refers to the likelihood that a system will perform correctly over time. Redundancy increases reliability because it reduces the chance that any single failure cascades into total system failure. These two terms, fault tolerant and reliable, are related but distinct. Fault tolerance is about surviving failure. Reliability is about the overall probability of correct performance. Don't conflate them on the FRQ. How the Internet uses redundancy. Here's a beautiful real-world example: the Internet itself. The original ARPANET, the predecessor to today's Internet, was literally designed by the U.S. Department of Defense with fault tolerance as a primary goal. The thinking was, if a nuclear strike takes out one city's infrastructure, can military communications still route around the damage and get through? The answer the engineers built into the system was yes, because of packet switching and redundant pathways. When you send a message across the Internet, it gets broken into packets, and each packet can take a completely different route from your device to the destination. If one router goes down, packets simply take another path. The routers themselves are constantly updating their routing tables to reflect which paths are currently available. This dynamic rerouting is the living, breathing implementation of fault tolerance, and the College Board expects you to connect this back to the concept of packet switching from earlier in Unit 4. Reading and drawing network diagrams. For the AP exam, you absolutely must be comfortable interpreting network diagrams. Picture a simple diagram with 5 nodes, let's call them A, B, C, D, and E, connected by various edges. If node A connects only to node B, and node B connects to everything else, then removing node B completely isolates node A. That network is not fault tolerant with respect to node failure. But if A is also connected directly to C, then removing B still leaves A able to communicate through C. That's the redundancy that makes the network robust. When the exam asks you to identify whether a network is fault tolerant, trace the paths explicitly. A common wrong answer trap is seeing a network that looks dense and assuming it's fault tolerant without actually checking. The trap question might show you a network where most nodes are richly connected, but one critical node sits like a bridge, the only connection between two clusters. That node is called a single point of failure, and its presence means the network is not fully fault-tolerant. Circle single points of failure on your scratch paper. The exam loves them. The trade-offs of redundancy. Now, nothing in engineering comes free, and the AP exam will sometimes probe your understanding of the costs of redundancy. Adding redundant paths and components means spending more money on hardware, more energy running additional systems, and more complexity in managing the network. This is a genuine trade-off: increased fault tolerance versus increased cost and complexity. The College Board frames this as a design consideration. When a question asks what is a disadvantage of redundancy in networks, the answer they're looking for is cost or complexity, not some technical failure mode. Also worth knowing, redundancy doesn't protect against every failure scenario. If two paths share a common physical cable underground, cutting that cable eliminates both paths simultaneously. True fault tolerance requires that redundant paths be genuinely independent. This is an edge case that appears occasionally. The exam might describe a situation where a network appears to have multiple paths, but they all share a single vulnerable point of failure. Connections to other units. This topic threads beautifully into several other areas you've studied. From Unit 4's discussion of the Internet, redundancy is why packet switching is superior to circuit switching for resilience. Packets reroute dynamically, while dedicated circuits have no fallback. From Unit 5, when you think about beneficial effects of computing, the reliability of networked systems enabled by redundancy is what makes the Internet a stable platform for global communication and commerce. And from Unit 2's discussion of data storage, redundancy also shows up in how data is backed up across multiple servers, which connects to the broader idea of data integrity and availability. The bottom line the College Board wants you to internalize is this: redundancy is the design principle that makes fault tolerance possible, and fault tolerance is what allows systems to stay up and running even when the inevitable failures occur. Networks are designed with the assumption that things will break. The art is in building systems that survive those breaks gracefully. With a strong understanding of how networks handle failure, you're perfectly positioned to explore the broader implications of how the Internet was designed, including the open protocols and standards that make all of this interconnection possible in the first place. 4.9 Path redundancy and network reliability. Let's talk about something that affects your life every single day, even if you've never thought about it: why the Internet almost never goes down. Think about what happens when you're streaming a show and your neighbor accidentally cuts through a cable wire while gardening. You barely notice a hiccup. How is that possible? The answer is path redundancy, and it's one of the most elegant ideas in all of computer science. The core idea: multiple paths through a network. Imagine you're driving from Chicago to New York City. There isn't just one road connecting those cities. There are dozens of possible routes. If there's a massive accident shutting down Interstate 80, your GPS finds you an alternate path. You still get to New York. The Internet works exactly the same way. Path redundancy means that data traveling across a network has multiple possible routes to reach its destination. So if one path fails, the data can be rerouted through a different path without the user ever knowing something went wrong. The College Board wants you to understand this concept at two levels: the conceptual level and the structural level. Conceptually, redundancy increases fault tolerance, which is the network's ability to continue functioning even when individual components fail. Structurally, redundancy is achieved by having multiple connections between nodes in a network, so that no single node or connection is the only way to reach a destination. Fault tolerance and why it matters. Here's a term you absolutely must know for the exam: fault tolerant. A system is fault tolerant if it can continue operating correctly even when some components fail. The Internet was actually designed with fault tolerance in mind from its very beginning. The original ARPANET was built partly for military purposes, with the explicit goal of being able to survive partial destruction and still route messages. Think of fault tolerance like this. Imagine a bridge made of a single rope. If that rope snaps, you're stuck. Now imagine a suspension bridge with hundreds of cables. Even if a few snap, the bridge holds. A fault-tolerant network is like that suspension bridge. It's robust because the failure of any single connection doesn't bring the whole system down. For the AP exam, you need to be precise here. Redundancy does not eliminate failure, it mitigates it. Even a redundant network can fail if enough connections go down simultaneously. The exam sometimes presents scenarios where redundancy has limits, and students who understand this avoid falling into the trap of thinking redundancy makes a network indestructible. Visualizing network topology, graphs you must know. The AP exam expects you to interpret and reason about network diagrams. Picture a graph in the mathematical sense, where nodes represent devices like computers, routers, and servers, and edges represent the connections between them. When you look at such a diagram on the exam, you need to ask yourself, is there more than one path between any two nodes? When a network has multiple paths between nodes, removing a single edge doesn't disconnect the graph, meaning information can still flow. But here's the critical exam scenario. What happens when you remove a node entirely? If a single node is the only connecting point between two halves of a network, sometimes called a bottleneck or a single point of failure, then removing it disconnects the network. This is exactly the kind of diagram the College Board loves to test. You should be able to look at a simple network diagram and identify which nodes or connections, if removed, would make communication between two specific devices impossible. Practice drawing small networks with 5 to 7 nodes and tracing every possible path between two endpoints. Can you always find at least two distinct paths? If yes, the network is redundant for that pair. If no, you've found a single point of failure. Packet switching. The mechanism behind redundancy. Path redundancy only works because of how data actually travels across the internet, through a technique called packet switching. When you send a file or load a web page, that data is broken into small chunks called packets. Each packet travels independently through the network, potentially taking completely different routes, and then they're reassembled at the destination. This is the key connection to redundancy, because packets travel independently. Different packets from the same message can take different paths. If one path is congested or goes down mid-transmission, later packets get automatically rerouted. Compare this to the old telephone system, which used circuit switching. It reserved one dedicated path for the entire duration of a call. If anything failed along that path, the call dropped. Packet switching is fundamentally more resilient precisely because it exploits redundancy at the packet level. The College Board connects this topic directly to the broader idea of how the Internet handles scale and failure. You'll see packet switching come up again when discussing protocols like TCP/IP, and understanding that path redundancy is the reason packet switching works so beautifully will help you reason through unfamiliar questions. Common exam traps and misconceptions. Here are the traps you need to avoid. First, students often confuse redundancy with speed. More paths does not necessarily mean faster data transfer in every scenario. It means more reliable data transfer. Redundancy is about availability and reliability, not raw performance. Don't get baited by answer choices that conflate the two. Second, watch out for questions that describe a network where two nodes are connected and ask whether communication is still possible if one path fails. Always check whether there is literally any other path, direct or indirect, through intermediate nodes before concluding that communication fails. Students who only look at direct connections miss indirect routes and choose the wrong answer. Third, some students think that adding more redundant paths always helps. In theory, that's true, but the AP exam also expects you to understand cost and complexity trade-offs. More connections mean greater expense and more complex management. Redundancy is a deliberate design choice, not a free upgrade. Connecting this to the bigger picture. This topic ties directly into Unit 4's broader conversation about how the Internet was designed and how it has scaled to connect billions of devices. Path redundancy is one of the key reasons the Internet is described as decentralized. There is no single critical node whose failure would take the whole system down. That decentralization also connects to ideas in Unit 5 around the Internet's role in society, specifically why it's difficult for any one entity to fully control or censor Internet traffic. When you encounter any AP exam question about network reliability, fault tolerance, or Internet design philosophy, your mental framework should always return to this central insight. The Internet stays up because it was engineered to route around failure, and it does that by making sure data always has somewhere else to go. Coming up next, we'll explore how the internet handles the massive challenge of identifying every device on the planet. Because before a packet can find an alternate route, it needs to know where it's going in the first place. 4.10 Scalability of Systems. What is scalability? Really? Imagine you open a lemonade stand. On day one, you have 2 customers, a single pitcher, and everything runs perfectly. Now imagine your stand goes viral on social media overnight, and suddenly 500 people show up tomorrow morning. Do you have enough lemons? Enough cups? Can one person even take 500 orders before the ice melts? That moment of reckoning, when demand grows and you have to ask whether your system can keep up, is exactly what scalability is about. In AP Computer Science Principles, the College Board defines scalability as the ability of a system to handle increased workload or demand. A scalable system can grow, adding more users, more data, more transactions, without breaking down or requiring a complete redesign. When a system is not scalable, performance degrades, costs explode, or the whole thing simply crashes. Your job on the exam is to understand what makes systems scalable, why scalability matters, and the trade-offs involved in building systems that can grow. The 2 paths, vertical and horizontal scaling. Here's where the College Board wants you to know 2 distinct strategies, and mixing them up is one of the most common traps on the multiple choice section. The first strategy is vertical scaling, which means making a single machine more powerful. You upgrade the CPU, add more RAM, install a faster hard drive. Think of it like replacing your single lemonade pitcher with a giant industrial vat. You are still one stand, one point of operation, just bigger and more capable. Vertical scaling has a hard ceiling. There is only so much hardware you can physically cram into one machine, and at some point, the cost becomes astronomical for diminishing returns. If that one super machine fails, your entire system goes down. This is a critical edge case the AP exam loves to test. A vertically scaled system is a single point of failure. The second strategy is horizontal scaling, which means adding more machines that work together. Instead of one giant server, you have 10, 50, or 10,000 servers sharing the load. Back to Lemonade, instead of one massive vat, you open 50 stands across the city. Each stand handles its share of customers. If one stand shuts down, the other 49 keep serving. This is the approach used by companies like Google, Netflix, and Amazon. Horizontal scaling is generally considered more robust and more flexible, but it introduces new complexity. Now you need systems to distribute work across all those machines and keep them coordinated. The AP exam will not ask you to implement that coordination, but you absolutely need to know that horizontal scaling introduces the challenge of managing distributed systems, and that it removes the single point of failure problem. Why scalability is a systems design challenge. Scalability is not just about hardware. It sits at the intersection of software design, network capacity, storage architecture, and cost, and the College Board frames it explicitly as a systems thinking problem. When you increase the number of users on a platform, every layer of that system gets stressed. The servers processing requests, the databases storing data, the networks transmitting information, and the interfaces delivering results. A bottleneck at any single layer, say, a database that can only handle 100 queries per second, no matter how many servers you add, limits the scalability of the entire system. This is called a bottleneck, and recognizing where bottlenecks occur in a described system is a genuine MCQ skill. Connect this back to Unit 4's broader themes. The Internet itself was designed with scalability in mind. The packet switching model you studied in earlier sections allows network traffic to reroute dynamically, which is why the Internet does not collapse when one node fails. That architectural decision from the beginning made the Internet horizontally scalable by design. When you see a question about why the Internet can handle billions of users, the answer lives in that foundational design philosophy. Trade-offs and the cost question. Here's something the AP exam leans into heavily. Scalability always involves trade-offs. Scaling a system up, whether vertically or horizontally, costs money, energy, and engineering effort. Cloud computing platforms like Amazon Web Services or Google Cloud allow organizations to scale dynamically, paying only for the computing resources they actually use. This is the concept of on-demand scaling, sometimes called elasticity, and it is highly testable. The idea is that a system can automatically provision more resources when demand spikes, say during a holiday shopping rush, and release those resources when demand drops. This is more cost-efficient than permanently owning hardware powerful enough to handle the peak load you might only hit twice a year. The trade-off framing also connects to the College Board's recurring theme of benefits versus costs and intended versus unintended consequences. A question might describe a company that scales its servers horizontally and ask you to identify both a benefit, redundancy, no single point of failure, and a potential cost or challenge, complexity of coordination, increased energy use, higher software engineering overhead. Recognizing both sides earns you full credit on free response questions and steers you away from the overly simplistic MCQ traps that present scaling as purely positive. Common MCQ traps you need to dodge. The College Board is very fond of presenting a scenario where a system is experiencing slow response times and asking what solution would best address scalability. The trap answer often describes something that solves a different problem entirely, like improving the user interface or optimizing a single algorithm on one machine, when the real issue is that the infrastructure cannot handle the volume of requests. Train yourself to read scalability questions carefully and ask, is the problem about one machine doing one task slowly, or is it about many users overwhelming a system? Those call for different solutions. Another trap involves confusing scalability with reliability. A reliable system is one that works correctly and consistently. A scalable system is one that handles growth. These often go together, but they are not the same thing, and the exam will absolutely probe whether you know the difference. A system can be highly reliable for 10 users and completely unscalable when 10,000 users arrive. One more edge case worth noting. The AP exam sometimes describes a system where adding more servers does not improve performance, and asks you to explain why. The answer almost always points to a bottleneck, a resource that cannot be parallelized, like a single database that all servers must query, or a network link with fixed bandwidth. Knowing that scaling is only effective up to the constraint of the system's bottleneck is a nuanced, five-worthy insight. Connecting forward, scalability ties together everything you have learned in Unit 4 about how systems are built, how networks function under load, and why good design decisions made early have compounding effects as systems grow. As you move into the topics on cybersecurity and the impacts of computing, you will see that large-scale systems also create large-scale risks, and the design choices that make a system scalable can either amplify or reduce those vulnerabilities. 4.11 Bandwidth and Latency. The highway analogy that changes everything. Imagine you're trying to understand why your video keeps buffering even though you're paying for high-speed internet, or why a file transfers slowly even on a fast network. To answer those questions, you need two concepts that are absolutely essential for the AP exam, and, honestly, for understanding the internet at a deeper level than most people ever do. Those concepts are bandwidth and latency, and the College Board tests them in ways that trip up even well-prepared students. Let's fix that right now. Here's the analogy you need to tattoo into your brain. Think of data moving across a network like cars moving down a highway. Bandwidth is the number of lanes on that highway, how much data can travel simultaneously. Latency is how long it takes a single car to drive from one end of the highway to the other, the delay before information actually arrives. A 12-lane highway is glorious for moving lots of cars, but if that highway is 3,000 miles long, any single car still takes hours to arrive. That's the critical insight. Bandwidth and latency are independent variables. Having one doesn't guarantee the other. Defining bandwidth precisely. On the AP exam, bandwidth is defined as the maximum amount of data that can be sent in a fixed amount of time. College Board frames it in terms of bits per second, so you'll see units like kbps, kilobits per second, mbps, megabits per second, and Gbps, gigabits per second. Notice that's bits, not bytes. This is one of the exam's most reliable traps. When you see a file size given in megabytes, MB, and a transfer speed given in megabits per second, MBTeeps, you must convert. There are 8 bits in a byte, so a 40 megabytes file is actually 320 megabits. Divide 320 megabits by your bandwidth in MBTeeps, and you get the transfer time in seconds. Students who skip that conversion lose easy points. The formula you need is elegantly simple. Transfer time equals file size divided by bandwidth. Just make sure both values share units. If your bandwidth is 50 megabits per se and your file is 200 megabits, the transfer time is 200 divided by 50 equals 4 seconds. Straightforward, right? But here's where boundary conditions get interesting. What if you double the bandwidth? You halve the transfer time. Bandwidth and transfer time have an inverse relationship. The AP exam loves asking you to reason about proportional changes. If bandwidth doubles, what happens to transfer time? The answer is it's cut in half, assuming latency is negligible. That word assuming matters enormously, and we're about to see why. Defining latency, the silent killer of performance. Latency is the time it takes for a single piece of data to travel from its source to its destination. Think of it as the delay, the pause before anything actually happens. When you click a link and it takes a moment before the page starts loading, that pause is largely latency at work. College Board defines latency simply as the time between sending and receiving a signal, and it's typically measured in milliseconds. Latency comes from several real sources. The physical distance data must travel, the speed of electrical or optical signals, which, even near the speed of light, add up over thousands of miles, the number of routers and switches the data must pass through, and any congestion along the way. A common exam question will describe a scenario where bandwidth seems sufficient, but performance is still poor. That's your signal, literally, to think about latency. High bandwidth cannot compensate for high latency. This is the conceptual trap the College Board loves most. Here's a vivid way to feel the difference. Imagine you're sending 1,000 photos across the country. Bandwidth determines how quickly the photos can be loaded onto the truck. More bandwidth, bigger truck, loads faster. Latency determines how long the truck takes to drive to its destination, regardless of truck size. Los Angeles to New York takes roughly 40 hours. A bigger truck doesn't make it drive faster. Once you see it that way, you'll never confuse the two again. How they interact, and why both matter. For small files and quick requests, latency dominates performance. When you send a tiny request, like a DNS lookup or a simple API call, the bandwidth barely matters because there's almost no data to transfer. What slows you down is the round-trip time, which is pure latency. For large file transfers, bandwidth dominates once the data starts flowing, but you still pay the latency cost up front as an unavoidable startup delay. This interaction is why engineers and network designers can't just throw more bandwidth at every problem. Streaming a live video from a satellite, that satellite is 22,000 miles above Earth. Even at the speed of light, that's roughly 240 milliseconds of one-way latency, a nearly half-second round-trip delay. No amount of bandwidth cures that. This is also why applications like online gaming are exquisitely sensitive to latency. They call it ping, even on high-bandwidth connections. Connecting to the rest of the course. This topic connects directly to several other areas you'll be tested on. In your study of the Internet's architecture, bandwidth and latency explain why protocols like HTTP and TCP are designed with certain handshaking and acknowledgement mechanisms. Those mechanisms add round trips, which add latency. When you study fault tolerance and redundancy, understand that routing around a broken network path can increase latency even while maintaining bandwidth. And in Unit 5, when you encounter computational complexity and the idea that some problems can be solved faster using parallel computing, recognize that the underlying hardware improvements, faster networks, higher bandwidth, are exactly what make distributed computing viable. The College Board also connects bandwidth to the digital divide, which is a social implications topic in Unit 1. Communities with limited bandwidth don't just experience slower streaming, they face real educational and economic disadvantages. That's not a test trap. That's genuine context that sometimes appears in the FRQ scenarios asking you to reason about equity and access. The MCQ traps in summary. 3 traps appear repeatedly. First, the bits versus bytes confusion. Always check your units before calculating. Second, assuming that higher bandwidth automatically means faster perceived performance. It doesn't when latency is the bottleneck. Third, confusing what happens with small data versus large data. Small payloads are latency bound, large transfers are bandwidth bound. If an MCQ gives you a scenario where doubling the bandwidth doesn't improve performance much, the answer almost certainly involves high latency as the real constraint. With bandwidth and latency firmly in your toolkit, you're now ready to understand how the internet actually routes data across those networks, which brings us perfectly to our next topic: how packets find their way from sender to receiver, even when the path isn't obvious. 4.12 Hardware components: CPU, memory, storage. Let's take a step back and think about what's actually happening inside the device you're using right now. Whether it's a laptop, a phone, or a desktop tower humming in the corner of your room, every single computation, every click, every video frame, every text message flows through 3 fundamental hardware layers: the CPU, memory, and storage. Understanding how these 3 work together isn't just trivia for the AP exam. It's the foundation for understanding why programs run fast or slow, why your computer sometimes freezes, and how the digital world actually functions at a physical level. The CPU, your computer's brain, the central processing unit, or CPU, is where all the actual thinking happens. Think of it as a very fast chef in a tiny kitchen. The chef can only work on one recipe at a time, or in modern CPUs, a small handful at once, but the speed at which that chef chops, stirs, and plates is absolutely breathtaking. The College Board describes the CPU as the component that executes instructions, and that's exactly right. Every line of code you've ever written eventually becomes a machine-level instruction that the CPU fetches, decodes, and executes in a cycle called the fetch, decode, execute cycle. You don't need to memorize the hardware engineering details of that cycle for the exam, but you absolutely need to understand that the CPU is the processor of instructions, not the place where data lives long-term. The speed of a CPU is measured in hertz, specifically gigahertz in modern machines. A 3 GHz processor can perform roughly 3 billion clock cycles per second. When the AP exam asks you what component controls how fast instructions are executed, the answer is always the CPU. Don't get tripped up by questions that try to confuse the CPU with memory. The CPU processes, memory holds. Modern CPUs also contain multiple cores, which the College Board occasionally references. A dual-core CPU can genuinely work on 2 instruction streams simultaneously, which is a form of parallel computing. This connects directly to Unit 4's discussion of parallel versus sequential processing. So remember, more cores can mean more parallelism, and parallelism generally improves performance for tasks that can be divided into independent pieces. Memory, the workspace. Now here's where students get confused constantly, and the AP exam knows it. When we say memory in computer science, we almost always mean RAM. Random access memory. RAM is your computer's workspace, its scratch pad. Going back to our chef analogy, if the CPU is the chef, then RAM is the kitchen counter. The bigger the counter, the more ingredients and tools the chef can have spread out at once, and the faster they can work without having to constantly go back and forth to the pantry. RAM is volatile memory, which is one of the most important terms you need to know for this exam. Volatile means that when power is cut, when you shut down your computer, everything in RAM disappears, gone. This is why you lose unsaved work during a power outage. RAM holds the programs and data currently in use, giving the CPU fast, immediate access to what it needs right now. The College Board distinguishes RAM from ROM, read-only memory. ROM is non-volatile, meaning it retains its data without power. ROM typically holds firmware, the very low-level instructions your computer needs to start up before the operating system even loads. On the exam, if a question asks about memory that persists without power, think ROM. If it asks about memory that the CPU actively uses while a program runs, think RAM. A critical concept here is the relationship between RAM and performance. When your RAM fills up, the operating system starts using a portion of your storage drive as virtual memory, which is dramatically slower. This is why adding RAM to a computer often makes it feel snappier. You're expanding that kitchen counter so the chef doesn't have to keep running to the pantry. Storage, the pantry. Storage is where data lives permanently, or at least until you delete it. Your hard drive or solid-state drive, SSD, holds your operating system, your applications, your photos, your documents, everything that needs to survive after you turn the power off. Storage is non-volatile, just like ROM, but unlike ROM, it's designed to be rewritten freely. Think of storage as the pantry. It holds far more than the counter, RAM, ever could. But getting something from the pantry and onto the counter takes much more time than grabbing something already sitting in front of the chef. The College Board AP exam will test you on the hierarchy of speed and capacity across these three components, and this is where you want to be precise. CPU registers and cache, the very fastest, smallest memory built right into the CPU, are fastest. RAM is next, fast but limited. Storage is slowest but offers the most capacity. This hierarchy is sometimes called the memory hierarchy, and the general rule is the closer the storage is to the CPU, the faster and smaller it is, the farther away, the slower and larger. Common MCQ traps and exam pitfalls. The single most common trap on this topic is confusing RAM and storage. Students hear memory in everyday language and think of their phone's 64 gigabytes of memory, but that's actually storage. Technically, your phone has both RAM, a few gigabytes, volatile, for active tasks, and storage, 64 plus gigabytes, non-volatile, for your apps and photos. When the AP exam says memory, it means RAM unless otherwise specified. Read every question carefully. Another trap involves volatility. If a question describes data being lost when a device loses power, the answer involves volatile memory, RAM. If data survives a power loss, you're dealing with non-volatile storage or ROM. The exam loves this distinction. Questions about performance often try to trick you into thinking that upgrading storage makes programs run faster. It doesn't, not directly. What makes programs run faster is having enough RAM, so the CPU doesn't have to wait, having a faster CPU or enabling parallelism through multiple cores. Storage speed matters for loading and saving files, but once a program is loaded into RAM, storage speed is largely irrelevant until you save again. Connections to other units. This topic threads through the entire course. In Unit 1, when you studied abstraction, hardware was the lowest layer, the physical foundation beneath software, programming languages, and applications. In Unit 3, when you wrote programs and thought about efficiency, you were really thinking about how to use CPU time wisely. In Unit 5, when you explore the impact of computing innovations, the relentless improvement in CPU speed, RAM capacity, and storage density described by Moore's Law is exactly what enabled the digital revolution. Every time the exam asks why software can do more today than it could 20 years ago, part of the answer lives right here in hardware evolution. With a solid mental model of how the CPU, RAM, and storage work together as a system, you're perfectly set up to understand how data moves through networks, which is exactly where we're headed next. 4.13 Sequential versus Parallel Computing. Let's talk about one of the most practically satisfying topics on the entire AP exam, the difference between sequential and parallel computing. This is one of those concepts where, once it clicks, you'll start seeing it everywhere, in your smartphone, in weather forecasting, in how Netflix renders your video. And the good news is that the College Board tests this in a very predictable way. So if you understand the core ideas deeply, you can absolutely nail every question they throw at you. The core distinction, one line versus many lanes. Picture a grocery store checkout. In sequential computing, there's only one register open and every customer, every task has to wait in that single line. Each task is completed one after another in order. Simple, predictable, but potentially slow when the line gets long. Parallel computing is like the store opening up 10 registers at once. multiple tasks run simultaneously, dramatically cutting down total wait time. That's the heart of this topic. More precisely, sequential computing is a computational model where operations are performed one at a time, in order, on a single processor. Each step must finish before the next begins. Parallel computing, on the other hand, distributes tasks across multiple processors or multiple cores of a single processor so that different parts of a problem can be worked on at the same time. Speed up and the key formula. Here's where the math comes in, and this formula is something you absolutely must be comfortable with for the exam. When you parallelize a task, the goal is to reduce the total time it takes. The College Board wants you to understand how to calculate the time it takes to complete a task using parallel processing versus sequential processing. The basic idea is this. If you have a program made up of several tasks, some of those tasks can be parallelized, run simultaneously, and some cannot. Tasks that depend on each other's outputs must still run sequentially, even in a parallel system. So the total time for a parallel solution equals the time spent on the sequential parts plus the time spent on the longest parallel path. Here's the formula you need to internalize. Imagine you have tasks that run one after another and tasks that can run simultaneously. The total time is the sum of all sequential task times plus the maximum time among all parallel tasks running at the same time. In other words, total time equals sum of all sequential task times plus longest parallel task chain. You're not adding up all parallel task times, only the longest one counts, because all the others finish while that longest one is still going. Drawing the diagram task timelines. The College Board loves to present these problems visually, so let's talk about the diagram you need to be able to read and draw. Picture a horizontal timeline. Sequential tasks are drawn one after another, like beads on a string. Each one starts only when the previous one ends. Parallel tasks are drawn as separate horizontal bars stacked vertically on that same timeline, all starting at the same moment. The total time elapsed for the parallel section is only as long as the single longest bar. When you add up all the sequential sections and add the longest parallel block, you get your total runtime. Practice drawing this. Sequential sections as a chain, parallel sections as stacked horizontal bars with a bracket showing their combined duration equals only the longest one. The concept of speed up. Speed up is simply the ratio of how long a task takes sequentially versus how long it takes with parallel processing. The formula is speed up equals sequential time divided by parallel time. If a program takes 100 seconds sequentially but only 40 seconds with parallelism, the speed up is 2.5, meaning the parallel version is 2.5 times faster. This shows up frequently on the multiple choice, often with a table of tasks and times, asking you to calculate the speed up. A critical exam trap here. Students often assume that using twice as many processors means the program runs twice as fast. It doesn't, because of those sequential portions that can never be parallelized. This is known as Amdahl's law in computer science, though the AP exam doesn't use that name. The key principle is that the sequential parts of a program limit how much speed-up parallel computing can achieve. No matter how many processors you add, those bottleneck steps still take the same amount of time. When can't you parallelize? This is crucial. A task can only be parallelized if it doesn't depend on the result of another task that hasn't finished yet. When task B requires the output of task A, task B must wait. These are dependent tasks, and they stay sequential no matter how many processors you have. Independent tasks, however, are free to run side by side. The AP exam will describe a set of tasks with dependencies listed and ask you to figure out what the minimum possible completion time is. Always identify which tasks are independent first. Then figure out which dependent tasks form the critical path, the longest chain that can't be shortened by adding more processors. Real-world connections and applications. Think about rendering a 3D animated film. Each frame can be calculated independently of the others, so studios use render farms with thousands of processors working in parallel. Or think about training a machine learning model. The data is split across processors so multiple pieces are analyzed simultaneously. Weather forecasting. genomics research, video encoding, all of these rely on parallel computing to handle enormous datasets in reasonable time. When the AP exam asks about use cases, remember that problems that can be broken into independent subtasks are the best candidates for parallelization. Common exam traps to avoid. The most common wrong answer trap is confusing total processor work with total elapsed time. If 3 tasks taking 4, 5, and 3 seconds run in parallel, students often add them up and say the parallel time is 12 seconds. Wrong. The elapsed time is 5 seconds because all 3 run simultaneously and the longest one finishes last. Only add up parallel times when tasks are sequential. Take the maximum when they run simultaneously. Another trap. The exam might describe a situation where adding more processors doesn't help. If a program is 100% sequential, every step depends on the previous, then parallel computing offers zero benefit. You must recognize that limitation. Also watch for questions about the trade-offs. Parallel computing requires more resources, more complexity in programming, and can introduce issues with data consistency when multiple processors access the same data. Sequential computing is simpler and perfectly appropriate for small or inherently ordered tasks. Connections to other units. This topic ties directly to Unit 4's broader themes of how computers work and how the Internet distributes processing. It also connects to Unit 2's discussion of algorithms and efficiency. Parallel computing is one strategy for improving the performance of algorithms on large datasets. When you studied big O notation informally or considered why some problems are computationally hard, that context feeds right into why parallelism matters. Understanding the limits of parallel computing also previews the concept of undecidable problems later in the course. Some problems simply cannot be sped up, no matter how much hardware you throw at them, just as some problems have no algorithmic solution at all. With sequential and parallel computing now firmly in your toolkit, you're ready to think about how computing power scales up to tackle the largest problems humans face. And that naturally leads us into our next discussion of how systems and networks handle the distribution of that computational work at scale. 4.14 Benefits and limitations of parallel computing. Let's talk about something that affects nearly every device you use, from your laptop to your phone, to the server farms powering your favorite streaming service. Parallel computing sounds intimidating, but once you understand the core idea, it clicks almost immediately. So grab your coffee, settle in, and let's break this down together. The core idea: divide and conquer. Imagine you're moving into a new apartment. You could carry every single box yourself, one at a time. That's sequential computing. Or you could call 10 friends, hand each one a few boxes, and get the whole job done in a fraction of the time. That's parallel computing. At its heart, parallel computing means breaking a large computational problem into smaller subproblems and solving those subproblems simultaneously using multiple processors or computing resources. The College Board definition you need to lock in is this: parallel computing is a computational model where multiple processors execute portions of a program simultaneously. The goal is to use idle hardware resources to speed up overall completion time. This is distinct from sequential computing, where tasks are executed one after another, in order on a single processor. You absolutely need to know both terms and be able to contrast them. This comparison shows up constantly on the exam. Speed up and the parallel portion, your key formula. Here's where it gets precise, and this is the part that trips up so many students on MCQs. The AP exam expects you to understand that not every part of a program can be parallelized. Some tasks are inherently sequential. They depend on the result of a previous step before they can begin. Think about making a sandwich. You can't spread peanut butter until the bread is sliced. That step is sequential no matter how many helpers you have. The formula you must know is the concept behind Amdahl's law, though the AP exam won't always name it. The idea is this: if a program has a portion that can be parallelized and a portion that cannot, the overall speedup is limited by the sequential portion. Let's say a task takes 60 minutes total. 40 minutes of it can be parallelized and 20 minutes must remain sequential. Even if you had infinite processors and completed the parallel portion in 0 time, the program still takes at least 20 minutes. You cannot parallelize your way out of sequential dependencies. That's the critical boundary condition the exam loves to test. The College Board expresses this with a direct comparison. The speed-up of a parallel solution is calculated by dividing the time the sequential solution takes by the time the parallel solution takes. If a sequential program takes 100 seconds and your parallel version finishes in 25 seconds, the speed-up is 4x. Straightforward, but watch for edge cases where students assume more processors always means proportionally more speed-up. It doesn't because of that sequential bottleneck. Visualizing the timeline, the diagram you must know. Picture a horizontal timeline. For a sequential program, tasks are lined up one after another like train cars on a single track. Task A finishes, then task B begins, then task C. For a parallel program, imagine multiple tracks running side by side. Task A, Task B, and Task C each run on their own track simultaneously. The overall completion time is determined by whichever track finishes last, not by the sum of all tasks. This is exactly the kind of diagram the exam may describe and ask you to interpret. When you look at a parallel execution diagram, always identify which tasks run concurrently, which tasks are sequential, and what the critical path is, meaning the longest chain of dependent tasks that determines the minimum possible completion time. Benefits. Why we bother? The benefits of parallel computing are real and significant. First, it can dramatically reduce the time needed to complete large-scale computations. Weather modeling, genomic research, training AI systems, rendering movie special effects, none of these would be feasible in reasonable timeframes without parallelism. Second, parallel computing lets us solve problems of a scale that would simply be impossible sequentially. The datasets involved in modern machine learning, for example, are so enormous that even the fastest sequential processor would take years. From a hardware standpoint, modern computers almost universally have multi-core processors, meaning multiple CPUs on a single chip. Your phone likely has 6 or 8 cores. This hardware reality makes parallel programming not just a theoretical option, but a practical necessity for efficient software. Limitations. The honest trade-offs. Here's where students often lose exam points. They know the benefits but underestimate the limitations. First, and most importantly, not all problems can be parallelized. Any task where each step depends on the output of the previous step is inherently sequential. Calculating compound interest year by year, for instance, you can't compute year 3 until you know year 2's balance. Second, parallel computing introduces overhead, the coordination cost of splitting a task, distributing it across processors, and then collecting and combining the results. For small problems, this overhead can actually make parallel solutions slower than sequential ones. The exam loves this counterintuitive edge case. If the problem is small enough, parallelism hurts performance. Third, parallel programs are significantly harder to write, debug, and reason about. When multiple processors are modifying shared data simultaneously, you get problems like race conditions, where the outcome depends on the unpredictable timing of which processor updates data first. The AP exam won't ask you to write parallel code, but you should know that this complexity is a genuine limitation. Common MCQ traps to avoid. The number one trap is assuming that doubling the processors always doubles the speed. It doesn't because of the sequential portion. A close second is assuming parallel computing is always better for small, simple tasks. Sequential is often faster because parallelism has overhead. Third, students confuse parallel computing with distributed computing. They're related but distinct. Distributed computing involves multiple separate computers communicating over a network. Parallel computing typically refers to multiple processors within a single system or closely coordinated systems. The College Board uses both terms, so don't conflate them. Finally, remember that the speed up achieved by parallelism is bounded. There is always a theoretical maximum determined by the non-parallelizable portion of the task. If 50% of your program is sequential, you can never achieve more than a 2x speedup, regardless of how many processors you add. Connections to other units. This topic connects directly to your understanding of algorithms and efficiency from Unit 3. Just as you evaluated the efficiency of sequential algorithms using concepts like time complexity, here you're evaluating the efficiency of parallel strategies. It also ties into Unit 5's discussion of the Internet and distributed systems, where parallel processing across multiple servers is foundational to how large-scale services function. Anytime you think about scalability, can this system handle more users, more data, more complexity? Parallel computing is part of the answer. As you move into the final stretches of Unit 4, keep this framing in mind. Every computing system is a balance between what the hardware can do and what the software architecture allows. That tension between capability and limitation is exactly what the next topic explores. 4.15 Parallel and Distributed Computing. The big picture, why this topic matters. Imagine you're at a restaurant, and a single chef has to cook every dish for every table alone. As the crowd grows, dinner takes forever. Now imagine that same restaurant hires 20 chefs, each handling a different station. Suddenly, hundreds of dishes fly out of the kitchen at once. That's the core intuition behind parallel and distributed computing, and it's one of the most heavily tested conceptual areas on the AP-CSP exam. College Board loves this topic because it sits at the intersection of systems thinking, algorithmic efficiency, and real-world problem solving. So let's make sure you own it completely. Sequential versus parallel computing. The AP exam draws a sharp line between sequential and parallel computing, and you need to be crystal clear on both. In sequential computing, tasks are carried out one after another in order on a single processor. Think of it like reading a book. You finish page 1 before page 2, no exceptions. In parallel computing, a problem is broken into smaller subproblems, and those subproblems are solved simultaneously on multiple processors. The chef's analogy fits perfectly here. The appetizers, entrees, and desserts cook at the same time on different burners. The AP exam expects you to understand that parallel computing can potentially reduce the time it takes to solve a problem. But, and this is a critical distinction, not all problems benefit equally from parallelization. Some tasks are inherently sequential, meaning step 2 cannot begin until step 1 is completely finished. Washing your hair is a good example. You must shampoo before you rinse. No amount of extra processors speeds that up. This concept is sometimes called a sequential bottleneck, and recognizing it is key to answering MCQs correctly. Speed up and efficiency, the formula you must know. Here's where the math comes in, and you will see this on the exam in some form. The speed up of a parallel solution compared to a sequential one is calculated as the time it takes to run the program sequentially divided by the time it takes to run it in parallel. Written out, speed up equals sequential time divided by parallel time. So if a task takes 100 seconds sequentially and 25 seconds with parallel processing, the speed up is 4, meaning the parallel version is 4 times faster. Now here's the trap the AP exam loves to set. Speed up is never unlimited. Even if you throw infinite processors at a problem, the parts that must run sequentially will always impose a ceiling on how fast you can go. This idea is captured by Amdahl's law in computer science. Though College Board doesn't require you to cite it by name, they just expect you to understand the concept. If 50% of your program must run sequentially no matter what, you can never achieve more than a 2x speedup, period. Watch for MCQ answer choices that claim parallel computing can always cut runtime proportionally. That's the trap. The correct answer always acknowledges the sequential portion as a limiting factor. Distributed computing, spreading the work across the network. Parallel computing usually refers to multiple processors inside one machine. Distributed computing takes the concept further. It spreads computation across multiple computers connected by a network, often the Internet itself. Think of the SETI at Home project, where millions of personal computers around the world collectively analyzed radio telescope data searching for extraterrestrial signals. No single supercomputer could have processed that volume of data affordably. Instead, the problem was divided into chunks, sent out to volunteers' computers, processed independently, and the results sent back. College Board wants you to understand that distributed computing solves two related problems. It enables computation at scales no single machine could handle, and it provides redundancy, meaning if one computer fails, others continue working. This connects directly to Unit 4's discussion of fault tolerance in networks. A system spread across many nodes is more resilient than one that depends on a single point of failure. How to think about parallel tasks on the exam. The AP exam frequently gives you a scenario with multiple tasks and asks you to figure out the total execution time given a certain number of processors. Here's your decision framework. First, identify which tasks are independent. They can run simultaneously. Then identify which tasks are dependent. They must wait for another task to finish. Draw a simple timeline in your scratch space. Put independent tasks side by side on parallel rows, and put dependent tasks end-to-end on the same row. The total time is determined by the longest path through that timeline, which computer scientists call the critical path. For example, if you have 4 tasks, A takes 10 seconds, B takes 20 seconds, C takes 5 seconds, and D must wait for both A and B before it can start. Then A and B can run in parallel, finishing in 20 seconds, the longer of the two, and then D runs after that. The total time is 20 plus D's duration, not 10 plus 20 plus 5 plus D's duration. This kind of calculation appears regularly on both MCQs and free response questions, so practice sketching those timelines until they feel automatic. Common misconceptions and MCQ traps. Several wrong answer patterns show up repeatedly, and knowing them in advance is like having a cheat sheet. First, students often assume that doubling the number of processors always halves the runtime. It doesn't, because of sequential bottlenecks. Second, some students confuse parallel and distributed computing as if they're the same thing. They're related but distinct. Parallel typically means multiple processors on one machine sharing memory, while distributed means multiple machines communicating over a network. Third, don't assume distributed computing is always faster. The overhead of sending data across a network can actually slow things down for small problems. Parallel and distributed approaches are most beneficial when the problem is large enough that the coordination costs are outweighed by the gains. Connections to other units. This topic connects beautifully to other parts of the course. The concept of algorithmic efficiency from Unit 3 is directly relevant. Parallel computing doesn't change the algorithmic complexity class of a problem, but it can dramatically change real-world runtime. The network concepts from earlier in Unit 4, including how the Internet routes data and tolerates failure, underpin how distributed systems actually function. And when you think about the potential of computing from Unit 7, the societal implications of distributed computing, crowdsourcing computation, cloud computing, data privacy, are all fair game for AP exam questions about beneficial and harmful effects of technology. Wrapping up. The heart of this topic is a simple but powerful idea. Breaking big problems into smaller pieces and solving them simultaneously makes computation faster and more capable, but physics and logic impose real limits on how much you can gain. Understand the sequential bottleneck, practice the speed-up formula, sketch those parallel timelines, and you'll be in excellent shape for any question College Board throws your way. With parallel computing under your belt, you're ready to zoom out even further as we explore how humans and machines interact with the digital world through the lens of beneficial and harmful impacts of computing in society. 4.16. Distributed computing and cloud computing. Let's talk about something you already use every day without thinking about it, the cloud. When you save a photo to iCloud, stream a show on Netflix, or collaborate on a Google Doc with a classmate in real time, you are interacting with systems that span thousands of machines across the globe. That's exactly what this section is about, how modern computing spreads work across many machines, and why that matters enormously for the AP exam. What is distributed computing? Distributed computing is the practice of using multiple computers connected through a network to solve a problem together. Think of it like a group project. Instead of one person doing all the work, you split the tasks among teammates so everything gets done faster and more reliably. On the AP exam, College Board defines this precisely. A distributed system is one where the components are located on different networked computers that communicate and coordinate their actions by passing messages to each other. The critical insight here is parallelism. When a task can be broken into smaller independent subtasks and assigned to different machines simultaneously, the total time to completion drops dramatically. This is called parallel computing in the AP curriculum, and you need to understand how it differs from sequential computing. In sequential computing, tasks happen one after another. Step 1 finishes, then step 2 begins. In parallel computing, multiple tasks run at the same time on different processors or machines. The AP exam loves to test whether you can identify which type is happening in a given scenario, so pay attention to whether steps depend on each other. If step B needs the result of step A, those two steps cannot be parallelized, they must remain sequential. Here's an analogy that makes this stick. Imagine you're baking a meal for a dinner party. Boiling water and chopping vegetables can happen at the same time, that's parallel. But you cannot frost a cake before the cake has baked, that's sequential. The AP exam will give you scenarios and ask you to identify the minimum time required to complete a task when work is divided optimally. So practice recognizing which subtasks are independent. The speed-up formula, know this cold. College Board expects you to understand the concept of speed-up in parallel computing. The key idea is this: even when you add more processors, there is always some portion of a task that must run sequentially and cannot be parallelized. This means there's a theoretical limit to how fast you can make a program by adding more hardware. On the AP exam, you may be given a table or description where some portion of work takes a fixed amount of time regardless of how many processors you use. If a task has a sequential component that takes 10 minutes and a parallelizable component that takes 20 minutes, running it on 2 processors reduces the parallel portion to 10 minutes, making the total 20 minutes. But adding 100 processors still cannot reduce the total below 10 minutes because of that irreducible sequential bottleneck. The exam does not require you to calculate Amdahl's law by name, but it absolutely tests this concept. The idea that increasing processors has diminishing returns and cannot eliminate the sequential portion. Cloud computing, your virtual data center. Now let's zoom into cloud computing specifically, because this is where most students pick up easy points or lose them to careless mistakes. Cloud computing means accessing computing resources, servers, storage, databases, software over the internet, on demand, rather than owning and maintaining physical hardware yourself. College Board identifies 3 things the cloud provides: on-demand access, resource pooling, and scalability. Think of it like electricity. You do not own a power plant. You plug into the grid and pay for what you use. Cloud computing works the same way. Companies like Amazon, AWS, Google, GCP, and Microsoft Azure own enormous data centers and rent out computing power the way a utility company sells electricity. If your website suddenly goes viral, you can scale up, request more computing power instantly without buying new servers. When traffic dies down, you scale back and stop paying for what you do not need. For the AP exam, you need to know the specific benefits College Board emphasizes. Cloud computing enables collaboration. Multiple users in different locations can access and work on the same data simultaneously. Think Google Docs. It enables access from anywhere because data lives on remote servers rather than a single local machine. It shifts the burden of maintenance, security updates, and hardware failure to the cloud provider. And it enables redundancy. Your data is typically stored in multiple locations, so that even if one data center has a fire or loses power, your files survive. This redundancy is a key reason. Cloud storage is considered more reliable than a single personal hard drive. Parallel versus distributed. Don't confuse these. A common trap on the MCQ section is conflating parallel computing with distributed computing. They overlap, but are not the same thing. Parallel computing can happen on a single machine with multiple processors or cores. Your laptop does this every time it runs multiple programs. Distributed computing specifically involves multiple machines connected by a network. The AP exam may describe a scenario involving many networked computers and ask which term applies. The answer is distributed computing. If the scenario describes one computer using multiple cores simultaneously, that is parallel computing on a single system. Both can be used together, and in the real world they usually are, but you need to keep the definitions clean in your mind. Connections to other units. This topic connects directly to what you have studied in networking, Unit 4's earlier sections. The Internet itself is the infrastructure that makes distributed computing possible. Packets travel across routers and switches so that your laptop in Chicago can communicate with a server in Oregon in milliseconds. It also connects to Unit 5 on the impact of computing, where you will think about how cloud computing changes economic access to technology. A small startup can now afford computing power that would have required millions of dollars of hardware 20 years ago, fundamentally democratizing what it means to build software. College Board loves to link distributed computing to these broader societal impacts, so be ready to discuss both the technical and ethical dimensions. The most common MCQ trap in this section is assuming that more processors always means faster results. Remember the sequential bottleneck. Adding infinite processors cannot eliminate the irreducible sequential steps. When you see an answer choice that says adding more processors will always reduce the runtime, that is almost certainly wrong. Up next, you will explore how these systems, distributed, cloud-powered, and globally connected, raise profound questions about data privacy, security, and the digital divide, which is exactly where Unit 5's exploration of the impacts of computing begins. 4.17 Computing Efficiency and Resource Allocation. Why this topic matters more than you think. Let's start with a scenario you already understand. Imagine you're trying to cook Thanksgiving dinner for 20 people. You could cook every dish one at a time, turkey first, then stuffing, then pie, or you could use every burner, both oven racks and your slow cooker simultaneously. The second approach gets dinner on the table in a fraction of the time, not because you're working harder, but because you're working smarter with the resources you have. That tension between doing things sequentially versus simultaneously, and between using resources wisely versus wastefully, is exactly what AP Computer Science Principles means when it talks about computing efficiency and resource allocation. Sequential versus parallel processing. The College Board wants you to have a solid conceptual grip on two fundamental execution models. In sequential computing, tasks are performed one after another in order. Each step waits for the previous one to finish before it begins. In parallel computing, a problem is broken into smaller pieces, and multiple processors or computing units work on those pieces simultaneously. The difference matters enormously when you're estimating how long a process takes. Here is the key formula you need to have down cold. If you have a task that takes a total of t units of time to complete sequentially, and you can parallelize some portion of it, the time saved is the difference between the sequential time and the parallel time. The AP exam loves to give you a table of subtasks with individual time values and ask you to calculate the total time under sequential versus parallel conditions. Let's say you have 5 tasks. Task A takes 5 seconds. Task B takes 3 seconds. Task C takes 4 seconds. Task D takes 2 seconds. And Task E takes 6 seconds. Sequentially, the total time is simply the sum. 5 plus 3 plus 4 plus 2 plus 6 equals 20 seconds. Now, if you can run all 5 tasks in parallel on 5 separate processors, the total time is determined by the longest single task, which is Task E at 6 seconds. The remaining tasks finish earlier and just wait. That ceiling value, the maximum individual task time, is your bottleneck under perfect parallelism. This is one of the most common MCQ traps on the exam. Students instinctively want to divide the total time by the number of processors. Don't do that. Parallel time equals the duration of the longest task, assuming all tasks can genuinely run simultaneously, and none depends on another. If dependencies exist, if Task C can't start until Task F finishes, then you have to account for that chain before applying parallel logic. Efficiency and the limits of parallelism. Now, here's the nuance the exam really probes. Not every problem can be perfectly parallelized. Some tasks are inherently sequential. You can't put on your shoes before your socks, no matter how many helpers you have. The AP exam may describe a scenario where only part of a process can be parallelized, and you need to calculate the overall speedup correctly. Think of it this way. Imagine a road trip where you spend 1 hour planning the route, which only one person can do, and then 4 hours driving, which, realistically, still only one person drives at a time, but let's say the preparation tasks within that window can be split. The planning hour is your irreducible sequential component. No amount of extra computing power eliminates it. This concept echoes what computer scientists call Amdahl's law, and while the AP exam won't ask you to use that name, the underlying principle that sequential bottlenecks limit the gains from parallelism absolutely shows up in the multiple choice. When you see an exam question that says something like, a program has two components, one that takes 10 seconds and cannot be parallelized, and one that takes 30 seconds and can be split across any number of processors, you need to handle the parallelizable portion separately and then add back the fixed sequential cost. If you have 3 processors for the parallelizable part, that 30 seconds becomes 10 seconds. Total program time, 10 equals 20 seconds. The trap is forgetting to add the sequential component back in. Resource allocation and real-world trade-offs. Efficiency isn't just about time, it's also about resources. The AP exam treats computing resources as things that can be scarce and must be allocated thoughtfully. These resources include processing power, CPU, memory, storage, bandwidth, and energy. A computing solution that's blazingly fast but consumes enormous memory may be impractical on a mobile device. A solution that's memory efficient but sluggish may be useless for real-time applications. This trade-off thinking is something College Board frames as part of responsible, effective computing design. You should also understand that adding more processors doesn't always produce proportional gains. Going from 1 processor to 2 might nearly halve your time. Going from 10 to 11 processors might save you almost nothing if most of the work is already finishing quickly and only one stubborn sequential task remains. This diminishing return concept is important for both MCQs and any FRQ that asks you to justify a design choice. Graphs and visual models you need to know. For the exam, be comfortable interpreting a bar chart or timeline diagram showing task durations under sequential versus parallel execution. In a sequential timeline, tasks stack end-to-end horizontally. In a parallel timeline, tasks align at the left edge and run simultaneously with the total width of the diagram equal to the longest single task. If you're asked to draw or interpret such a diagram, label each task clearly, mark the total completion time with a vertical line, and distinguish which tasks share the same time window versus which run in sequence due to dependencies. A connected concept from Unit 2 and Unit 3 is algorithmic efficiency. Specifically the idea that some algorithms are simply better suited to large-scale problems because they grow more slowly as input size increases. While this section focuses on hardware-level parallelism rather than algorithm design, the exam often connects the two. An efficient algorithm running on parallel hardware is doubly powerful. An inefficient algorithm doesn't become acceptable just because you throw more processors at it. Connecting to the broader course. This topic connects directly to Unit 3's exploration of algorithms and program efficiency, where you examined how problem complexity scales with input size. It also ties into Unit 4's discussions of the Internet and distributed computing, where multiple servers handling requests simultaneously is essentially parallel processing at global scale. On the FRQ, if you're asked to evaluate a computing solution, mentioning both algorithmic efficiency and hardware resource allocation shows the kind of layered thinking that earns full rubric credit. The single most important thing to take away from this section is the distinction between what parallelism can help and what it fundamentally cannot change. Sequential bottlenecks are real, dependencies matter, and the longest task always sets the floor for parallel completion time, not the average, and not the total divided by processor count. With that foundation in efficiency and resource allocation firmly in place, you're perfectly set up to explore how these principles play out at the network level, where data routing and bandwidth constraints create their own fascinating efficiency challenges. 4.18. The Internet and Cybersecurity Threats, Phishing, Malware, DDoS. Setting the scene, why cybersecurity matters. Imagine you wake up one morning to find your bank account drained, your emails sending spam to everyone you know, and your school's website completely offline. These aren't hypothetical horror stories. They're the real-world consequences of the 3 cybersecurity threats you absolutely need to master for the AP exam: phishing, malware, and distributed denial of service attacks, or DDoS. The College Board loves this topic because it sits at the intersection of technical knowledge and real human behavior, and that combination makes for some genuinely tricky multiple-choice questions. So let's walk through each threat the way a cybersecurity professional would actually think about it. Phishing, the art of the fake. Phishing is a social engineering attack, and that phrase social engineering is exactly how College Board frames it on the exam, so burn it into your memory. Social engineering means exploiting human psychology rather than technical vulnerabilities. The attacker isn't hacking your computer's code, they're hacking you. A phishing attack involves a malicious actor impersonating a trusted entity, your bank, your school, even a friend, through email, text, or a fake website, with the goal of tricking you into revealing sensitive information like passwords or credit card numbers. Think of it like this: a con artist doesn't pick your pocket. They convince you to hand over your wallet willingly. That's phishing in a nutshell. On the AP exam, you need to distinguish between regular phishing, broad, mass-distributed attacks sent to thousands of people hoping someone bites, and spear phishing, a targeted attack customized for a specific individual or organization, using personal details to seem more credible. The exam may give you a scenario and ask you to identify which type is occurring. If the attack is personalized, mentioning your name, your company, your recent purchase, that's spear phishing. If it's a generic "Dear customer, click here to verify your account" message, blasted out widely, that's standard phishing. The key defense concepts the College Board expects you to know are awareness and verification. You protect yourself by questioning unexpected requests for sensitive information and independently verifying the source through a known, trusted channel, not by clicking the link in the suspicious email itself. Malware, software that wishes you harm. Malware is short for malicious software, and it's an umbrella term covering several subcategories you need to know cold. The College Board uses malware as the overarching concept, but you should be fluent in its specific forms. A virus is malware that attaches itself to a legitimate program and spreads when that program is shared or executed. Think of it like a biological virus hitching a ride on a host cell. A worm, by contrast, doesn't need a host program at all. It self-replicates and spreads across networks independently, which is what makes worms particularly dangerous. A Trojan horse, or just Trojan, disguises itself as legitimate software. You think you're downloading a free game, but you're actually installing something that gives an attacker access to your system. That gift with something hidden inside. The analogy to Greek mythology is intentional and is worth remembering for conceptual clarity on the exam. Then there's ransomware, which is a type of malware that encrypts your files and demands payment for the decryption key. It's been responsible for shutting down hospitals, pipelines, and city governments in real life, and the College Board may use it in scenario-based questions. The key technical detail: ransomware uses encryption as a weapon, which ties directly back to the encryption concepts from earlier in Unit 4. Spyware secretly monitors your activity and sends data back to an attacker. Keyloggers, a specific type of spyware, record every keystroke you make, capturing passwords, credit card numbers, and private messages without you ever knowing. A common MCQ trap here is confusing a virus with a worm. Remember, a virus needs a host file and human action to spread. A worm spreads autonomously across a network without any host file. If a question describes malware spreading from computer to computer automatically with no user action required, that's a worm, not a virus. DDoS, overwhelming the system. A distributed denial of service attack works on a beautifully simple and brutal principle. If you flood something with more requests than it can handle, it stops working for everyone. Imagine a restaurant with 10 tables. On a normal night, customers come in, get seated, and eat. Now imagine someone reserves all 10 tables and never shows up. No one else can be served. That's a denial of service attack. Now imagine 1,000 people all doing it simultaneously from different locations around the world. That's a distributed denial of service attack, or DDoS. The distributed part is critical, and it's where botnets come in. A botnet is a network of compromised computers, often infected without the owner's knowledge through malware that an attacker controls remotely. These zombie computers can be directed to simultaneously flood a target server with traffic. Because the attack comes from thousands of different IP addresses, it's extremely difficult to block. The College Board wants you to understand that DDoS attacks don't steal data. They deny access to a service. That distinction matters on the exam. If a question asks what a DDoS attack accomplishes, the correct answer involves making a resource unavailable, not stealing information. The defense against DDoS involves strategies like rate limiting, capping how many requests a single source can make, traffic filtering, and using distributed infrastructure to absorb the load. But the College Board focuses more on your conceptual understanding of the attack than the technical defenses. Connecting to the bigger picture, these three threats don't exist in isolation on the exam. Phishing often delivers malware. You click a link, and a Trojan installs itself. Malware often builds botnets, which are then used for DDoS attacks. The College Board frequently presents multi-step scenarios where you need to trace the chain of events and correctly label each component. Additionally, these concepts connect directly to the broader themes of the Internet structure from earlier in Unit 4. The fact that the Internet is an open, trust-based system is precisely what makes these attacks possible. And they tie to the data and privacy discussions coming in Unit 5, where you'll think about who owns your data and how it gets compromised. One final exam tip. When you see the phrase, "which of the following is an example of a social engineering attack?" the answer will almost always involve phishing, because it targets human behavior rather than technical systems. Don't let technically complex answers distract you. The College Board is testing whether you understand that sometimes the weakest point in a security system isn't the code, it's the person sitting at the keyboard. With cybersecurity threats now in your toolkit, you're ready to move into the broader conversation about how data, privacy, user rights, and digital citizenship all intersect in our increasingly connected world. 4.19 Encryption and Data Security. Symmetric versus asymmetric. SSL/TLS. The lock and key problem. Imagine you want to pass a secret note to a friend across a crowded room, but everyone in that room can see exactly what you're writing. That's essentially the problem encryption solves. Every time you log into your bank account, buy something online, or even just check your email, your data is traveling across networks where, in theory, someone could intercept it. Encryption is the mathematical art of scrambling that data so that even if someone does grab it mid-flight, all they see is gibberish. For the AP exam, you need to understand not just that encryption works, but how it works, and specifically the critical difference between the two main types. Symmetric encryption. One key to rule them all. Let's start with symmetric encryption because it's the simpler concept. Picture a lockbox with a single key. You lock the box, send it to your friend, and your friend uses the exact same key to open it. That's symmetric encryption in a nutshell. Both the sender and the receiver use the same key to encrypt and decrypt the data. The College Board defines this as encryption, where a single shared key is used for both operations. Here's the elegant part. Symmetric encryption is fast and efficient, which is why it's still used today for bulk data encryption. But here's the fundamental problem. The AP exam loves to test you on, how do you safely share that key in the first place? If you send the key over the same insecure network you're trying to protect, an eavesdropper could grab the key and then decrypt everything. This is called the key distribution problem, and it's the central weakness of symmetric encryption. You'll want to have that phrase ready. If an MCQ asks why symmetric encryption is problematic for internet communication, the answer is always about this key sharing challenge, not about the strength of the encryption itself. Asymmetric encryption. The public mailbox model. Asymmetric encryption solves the key distribution problem in a beautifully clever way. Instead of one shared key, every user has a key pair, a public key and a private key. These two keys are mathematically related, but here's the critical rule you must memorize. Data encrypted with the public key can only be decrypted with the private key, and vice versa. Think of it like a special mailbox on the street. Anyone can walk up and drop a letter in. That's your public key. But only you have the key to open the mailbox and read those letters. That's your private key. You can hand your public key to literally anyone, post it on a website, shout it from a rooftop, and it doesn't matter. Because knowing the public key tells an attacker nothing useful about decrypting your messages. The AP exam will absolutely test whether you understand what stays secret and what can be shared. Your private key is never shared with anyone, ever. Your public key is freely distributed. A very common wrong answer trap is a question that implies you need to protect your public key. You don't. Another trap involves mixing up which key does the encrypting. When someone sends you a secure message, they encrypt it with your public key. You decrypt it with your private key. Don't let the exam flip this on you. Digital signatures and authentication. Here's where asymmetric encryption gets even more interesting, and where the AP exam often tests a concept students miss. Asymmetric encryption isn't just for secrecy, it's also used for authenticator authentication, proving that a message actually came from who you think it came from. In this use case, the sender encrypts a piece of data with their own private key. Anyone can decrypt it with the sender's public key, which means it's not secret, but it proves the message came from that sender, because only they possess the private key. This is the foundation of a digital signature. The College Board wants you to know that certificates and digital signatures use this reverse application of asymmetric encryption. SSL, TLS, the handshake that secures the web. Now let's zoom out and talk about SSL, which stands for Secure Sockets Layer, and its modern successor TLS, Transport Layer Security. When you see HTTPS in your browser's address bar or that little padlock icon, TLS is what's making that connection secure. The exam uses these terms, and you should know that SSL and TLS are effectively the same concept for AP purposes. TLS is just the updated, more secure version. Here's what makes TLS so elegant. It actually combines both types of encryption to get the best of both worlds. The process begins with what's called a handshake. During the handshake, asymmetric encryption is used to safely exchange a temporary symmetric key, solving the key distribution problem we talked about earlier. Once both sides have that shared symmetric key, the rest of the conversation switches to symmetric encryption, because it's much faster for large amounts of data. So TLS uses asymmetric encryption to establish trust, then symmetric encryption for speed. This hybrid approach is something the AP exam loves to test. If you see a question about why TLS uses both types, the answer involves both security of key exchange and efficiency of data transfer. Certificates and the chain of trust. One more concept you need for a 5 digital certificates. How does your browser know that the public key it just received actually belongs to, say, your bank, and not to an attacker pretending to be your bank? This is where certificate authorities, or CAs, come in. A certificate authority is a trusted third party that digitally signs certificates, essentially vouching that a public key really does belong to who it claims. Your browser comes preloaded with a list of trusted CAs. If a site certificate was signed by one of them, your browser trusts the connection. If not, you get that scary warning screen. The College Board frames this as the role of a trusted third party in securing communication. Connecting this to other units. This topic connects powerfully to Unit 5's discussions of the impact of computing, specifically around privacy, data security, and cybersecurity threats like man-in-the-middle attacks. It also ties into Unit 4's broader treatment of how data travels across networks and why protocols like HTTPS exist. When you see free response questions about the internet and privacy, you're almost always expected to discuss encryption as a safeguard. The most important MCQ discipline here is keeping symmetric and asymmetric encryption clearly separated in your mind. One key versus two, speed versus security, the shared secret versus the public-private pair. Get those distinctions locked in, and you'll navigate this section of the exam with confidence. Speaking of navigating systems and security, let's turn next to how the internet handles the threats that encryption is trying to defend against, including the world of cybersecurity attacks and the protocols designed to stop them. 4.20 Digital Certificates and Certificate Authorities. The problem of trust online. Imagine you receive a letter in the mail that claims to be from your bank. It looks official, the logo is there, the formatting seems right, but how do you actually know it's from your bank and not from someone trying to steal your account information? This is exactly the problem the internet faces every single time you visit a website. When your browser connects to what it believes is your bank's website, how does it know it's talking to the real bank and not an imposter? That's the problem. Digital certificates and certificate authorities were designed to solve, and understanding them is absolutely essential for your AP exam. What is a digital certificate? A digital certificate is essentially an electronic document that verifies the identity of a website, person, or organization online. Think of it like a passport, but for websites. Just as your passport is issued by a government authority and contains information that proves who you are, a digital certificate is issued by a trusted organization and contains cryptographic information that proves a website is who it claims to be. The College Board wants you to understand that digital certificates serve two primary purposes. They verify identity, and they enable encrypted communication. These two functions work hand in hand. The certificate contains the website's public key, which you'll remember from your study of public key cryptography, along with information about the site's identity and, critically, a digital signature from a trusted authority that vouches for the whole package. When your browser receives this certificate, it can use the trusted authority's public key to verify that the signature is authentic, which in turn confirms that the certificate belongs to who it claims to belong to. Certificate authorities. The trust hierarchy. This is where certificate authorities, or CAs, come in. A certificate authority is a trusted organization whose job is to verify the identities of websites and then issue digital certificates to those sites after verification. Think of certificate authorities as the notary publics of the internet. They're trusted third parties whose whole reputation is built on vouching for others' identities. The trust system works in layers. Your operating system and browser come preloaded with a list of root certificate authorities that are considered inherently trustworthy, organizations like DigiCert, Let's Encrypt, and others. These root CAs can then vouch for intermediate CAs, which in turn vouch for individual websites. This creates what's called a chain of trust. When your browser checks a website certificate, it follows this chain all the way up to a root CA it already trusts. If the chain is intact and the signatures all check out, you get that satisfying padlock icon in your browser's address bar. For the AP exam, you need to be crystal clear on this point. The security of the entire system depends on certificate authorities being trustworthy. If a certificate authority is compromised or starts issuing fraudulent certificates, the whole system breaks down. This is not a hypothetical concern. There have been real-world cases where certificate authorities were hacked or misbehaved, and it caused serious security crises across the internet. How the verification process actually works. Here's the step-by-step process your browser goes through, and you should be able to describe this for the exam. When you type a URL into your browser and hit enter, the web server sends back its digital certificate. Your browser checks the certificate's digital signature using the CA's public key. If the signature is valid, it means that CA genuinely issued this certificate and hasn't been tampered with. Your browser then checks that the certificate is valid, meaning it hasn't expired and hasn't been revoked. Finally, it checks that the domain name on the certificate actually matches the website you're trying to visit. All three checks must pass. If anyone fails, your browser throws up a warning that something is wrong. That warning screen you've probably seen, your connection is not private, is your browser telling you that one of these checks failed. This is one of the most important practical implications of this topic for the exam. A certificate warning doesn't necessarily mean a site is malicious, but it absolutely means you cannot trust the identity of the server you're connecting to. Common MCQ traps to avoid. The AP exam loves to test whether you understand the purpose of certificates versus the purpose of encryption itself. Here's the trap. Encryption prevents eavesdropping on your data in transit, but it does not by itself prevent you from securely sending your information to the wrong person. You can have a perfectly encrypted connection to a criminal server. Digital certificates solve the identity problem, making sure you're talking to who you think you're talking to, while encryption solves the confidentiality problem. Don't confuse these two related but distinct functions. Another common trap involves who issues certificates. Certificate authorities issue certificates to websites. Users don't issue their own certificates, at least not ones that will be trusted by default, and websites don't verify their own identity. That's the whole point. The verification comes from an independent, trusted third party. Connections to other units. Digital certificates connect deeply to the public key cryptography concepts you studied in Section 4.19. The certificate is essentially a container for a public key that comes with a trusted guarantee of authenticity. Without certificates, public key cryptography would still protect the content of your messages, but you'd have no way to verify that you had the right public key for the right person. This is called a man-in-the-middle vulnerability, which connects back to the broader cybersecurity threats covered in the network security sections. Certificates are also a core component of HTTPS, the Secure Web Protocol, which ties directly to the concepts of how the Internet works in the earlier parts of Unit 4. From an impact of computing perspective, which the College Board emphasizes throughout the course, certificate authorities represent a fascinating case study in how centralized trust systems create both security and single points of failure. The entire encrypted web depends on a relatively small number of root certificate authorities being reliable, and that's worth thinking about critically. The big picture. The elegance of digital certificates is that they solve a fundamentally human problem. How do we establish trust with strangers using mathematics and institutional reputation? Your browser can verify a certificate in milliseconds automatically without you doing anything at all. That seamless experience is the result of a carefully engineered system of public key cryptography and trusted third parties working together. As we move into the next section, we'll build on these ideas about network security and trust to examine broader cybersecurity practices and how individuals, organizations, and systems defend against the threats that make certificates necessary in the first place.